Okay. So let's get started. Okay. Yeah. We have this set of slides uploaded a couple of weeks ago already. So you guys should have like downloaded the slides from the Keras, by yourself. Okay. If you haven't done so, okay, please do it. Okay. And so after the introduction of after the previous set of slides, the getting started, we are finally ready to talk about the deep learning. Okay, so so what is artificial neural networks, or abbreviated as ANN? Okay, the first thing you may ask is, why do we talk about ANN? Because this class is deep learning, right? So the relationship between deep learning and artificial neural network, pretty much like they are basically like just another way to call the ANN is just another way to call deep learning. Okay, so it's because we want to look at the we want to create artificial intelligence, right? So it will be natural, very logical to look at the brain architecture. Because the animal, okay, including human, ourselves, okay, are the intelligent beings, right? So we can refer to when we want to create an intelligent system, right? So obviously, for human or for animal, okay, the brain is controlling the thinking, okay, the idea, okay. So we look at the brain architecture, okay, if you want to build an intelligent machine. So that is actually where artificial neural network gets its idea from. Okay, and but I want to emphasize that nowadays, okay, because originally, okay, artificial neural network actually gets so many ideas from the biological neural networks, but nowadays, okay, there are many places, okay, the researcher found that, okay, the brain neural network, okay, it's not so efficient. Okay, so the current design of artificial neural network, okay, in many places will be different than the biological neural network. We will talk about this in the future. Okay, so the ANN, the artificial neural networks, okay, are very the core of deep learning. Okay, it is we know they are versatile, powerful, stable, scalable. Okay, so nowadays we use the artificial neural networks, okay, to do many highly complex tasks for us. For example, the Google image use the ANN to classify billions of images. Okay, Apple Siri use ANN to do speech recognition. YouTube use ANN to recommend the videos for the customer. And not to mention, DeepMind, AlphaGo, okay, use ANN to beat the world champion in Go, in the game of Go. Okay, so all these tasks are achieved by ANN. Of course, you may say, oh, wait. The deep learning, AlphaGo. Isn't AlphaGo like designed by using like reinforcement learning? Well, there are ANN has many different flavors, as we will talk about in this class in the future. Okay, so the reinforcement learning, okay, used in AlphaGo is called the deep reinforcement learning, which also incorporate the artificial neural networks in the design. Okay, just want you to be aware of that. Okay, so artificial neural network were first introduced in 1943. Okay, so this is really not a new thing. Okay, ANN, it has been there for close to 70, how many? Close to 80 years, right? Close to 80 years already. Okay, so of course at that time, okay, because at that time very few people have deep understanding of the brain architecture. So this concept was, brought up by neurophysiologists. Okay, those doctors who work on the brain research. Okay, this guy called Warren McCulloch and the mathematician Walter Pitts. Okay, so this brain researcher collaborate with a mathematician, okay, to propose this ANN concept. Okay, so their ANN architecture obviously is very different from the current one. Okay, but at that time they are able to use their ANN architecture to solve the propositional logic. Okay, I will talk about their simplified ANN architecture, okay, later. Okay, I think hopefully today, okay, we are going to talk about this. Okay, just to give you an idea, okay, what an ANN in the old days looked like. Okay, so in the 1940s, okay, their research, because their research was already able to deal with propositional logic, okay, which is considered one of the difficult problems in computer science. Okay, so their success, okay, actually, okay, until 1960s, okay, led to the widely believe that we will be able to create artificial intelligence, okay, very soon. But this marks the first rise of artificial intelligence research, okay, from 1940s to 1960s. Okay, there were so many people dedicated to AI research. Okay, starting from MIT, Stanford, Carnegie Mellon, and then so many very famous universities have so many people working on AI, and at the end, in the 1960s, they proved to be fail. Okay, again, I will talk about why it doesn't work. Why it doesn't work? Okay, it is because they can prove for their AI model. Okay, for their AI model, there's a limitation. There's a limitation. They couldn't, for a little bit more complicated problem, they just couldn't solve it. Okay, so I will talk about this later. Okay, so in the 1980s, okay, people start to find out. Okay, remember I told you because they proved that there's a limitation for the early AI model. So people start to find out that we can design a more complicated AI model. Okay, basically, okay, let me put it this way. The original AI model is only one layer. You only have one layer of neurons. And they found out, okay, if we add more layers, we seem to be able to solve more complicated problems. Okay, because of this finding, okay, in the early 1980s, okay, to about 1990, about 10 years, okay, there will be a revival of interest in AI, okay. So again, like so many papers were written, okay, and obviously, as I told you, okay, because the architecture become deeper, we have more layers in the model, so the training become more and more difficult. Okay, so a lot of paper, talk about training techniques. Okay, so they were developed like in that period of time. But okay, about the year, about in the 1990s. Okay, a lot of alternative algorithms nowadays that we call them machine learning algorithms, okay, such as like the most famous one is SVM, okay, supported vector machine, okay. I mean they were invented in 1990s, okay, and people found out that okay, SVM perform much better than neural networks, okay. The neural network is difficult to train and perform worse than SVM. So people think like, well, why do we need to start with like artificial neural networks? So people gave up artificial neural networks, okay, and try to they embrace, different variations of the machine learning algorithm. I'm not sure. How many of you here took machine learning classes? There are so many different machine learning algorithms out there. Okay, we talked about, well, in the previous slides, we talked about linear regression. We talked about polynomial regression. You can consider them as like a machine learning algorithm as well. Okay, there are other famous ones such as decision tree. Okay. Naive Bayes, okay, methods, as well as like SVM, okay. These algorithms, they are faster, okay. They don't require like their performance are in general much better, okay, than the artificial neural network at that time. Okay. Why it is like that? I will talk about that in the next slide. Okay, in the next slide. Okay. So this is like because of that. Okay, the deep learning or ANN. Okay, becomes like obsolete, okay, you can say that, okay, in 1990s. Actually, I went to United States in 1993, okay, and at that time, okay, when I applied my graduate study in United States, in the research statement, I actually wrote that I want to do AI for like the game of Go, okay, because I like to play Go, okay, in my college years. So if sorry. Yeah, sorry, never mind. Okay. So if I stick to my plan, maybe I'll become one of the researchers for the AlphaGo. I don't know, maybe. But at that time, when I went to US, nobody studied artificial neural networks anymore. So I pretty much gave up that research. Okay, but who knows? After another couple of decades, I'll be here talking about artificial neural network again. Okay, so it's interesting, like very interesting thing to happen. Okay, so this is like a second wave of artificial intelligence. You can say the second wave of artificial intelligence. Okay, so now, okay, we are now witnessing another wave of interest in artificial neural network, or another wave of artificial intelligence. Okay, so so this is actually the third wave. The third wave. So you may ask, since the second wave of AI died, okay, because the ANN performed worse than machine learning model, so why is it so powerful nowadays? What's the difference? Okay, in the 1990s, okay, and now, well, the AI, you can say the AI, the third wave of AI is, it starts around like 2010, about that period of time. So what's the difference between these 20 years? What's the difference? Okay, let me put it this way. Okay, there are three differences. Okay, the first two are actually accidents. The last one is due to the researchers' effort, okay, in artificial neural network. Okay, the first one is that, okay, in the 1990s, okay, we don't have a lot of data. Okay, for deep learning model or for artificial neural networks, if you want to train an artificial neural network, you have to have sufficient amount of training data set. Okay. Unfortunately, at that time, in the 1980s and the 1990s, we don't have a good measure to collect data quickly. Okay. In the remember I told you, I went to the United States in 1993, right? At that time, I still remember we were using Netscape, okay, on the Sun workstation, okay, that were first connected to the internet for maybe like 1-2 years only. So in the 1993, the internet is in its infancy. Okay, we don't have World Wide Web. Okay, but nowadays, well, we can collect many tons of many different types of data through internet. Okay, for example, if you want the photos, the Instagram has so many photos waiting for you to collect. Okay, if you want to collect sensor data, okay, again, many IoT devices are actually online. Okay, there are many data sets freely available on the internet that you can download so easily. Okay, this is not the case in the 1980s or 1990 or even in the 1990s. Okay, the internet or World Wide Web is so mature nowadays. It makes the data collection much easier. Okay, I'm not saying data set is an easy task. I never say that. Okay, even though you can collect data, okay, but a lot of time it takes time to label your data set. Okay, and the labeling may take some time, and also the collected data may have noise, right? So how to prepare a good data set is still a question. Okay, but at least we have a way to quickly collect a large amount of data, which was not available like in the old days. So this is, of course, internet or World Wide Web was not invented because of the AI, right? We use World Wide Web, okay, all the time, but obviously World Wide Web was there, okay? The web was there. It's not because of the AI, okay? So this is the first accident. Okay, what's the second accident? In the old days, you know, like the 1980s and 1990s, okay, the computer is very weak. It's very weak, okay. You know, thanks to the Moore's law, okay, the computer's you know, performance doubles pretty much every couple of years, you know. So now, I mean, the computer becomes faster and faster, okay. But still, like, okay, if we stick to the traditional computer architecture, the AI is not going to be so easy to materialize. Okay, the training of the artificial neural network is still difficult. Okay, if we consider the current architecture, I mean or like traditional architecture of a computer. Okay, when I refer to traditional computer of architecture, I'm talking about the CPU. Okay, even for the CPU, the advanced CPU nowadays, do you use CPU to train the machine learning train the model? Probably not, right? Everybody know, like, if you want to train a neural network now efficiently, what do you need? GPU, right? So was the GPU designed for AI? No, it was designed for what? Huh? GPU stands for graphic processing unit, right? It was actually developed in the early 2000s. Okay, I think the first one is NVIDIA. Okay, NVIDIA. Okay, they want to speed up the process of like a graphical, you know, graphics, for gaming, especially for gaming. Okay, because people play games, they want the most sophisticated, like you know, the experience. Okay, from their monitor, obviously. Okay, so the refresh rate becomes higher and higher, and you know, the picture quality, okay, the resolution become higher and higher, right? And because of that, okay, I mean, they were thinking like, okay, if we can use like you know, the GPU, what's the difference between GPU and the CPU? GPU has so many cores, right? You can consider GPU as the collection of many small CPUs, and each small core basically deal with 1 pixel on your monitor. It will compute the color and the intensity for 1 pixel for your well, I'm sorry, let me get a phone call real quick. 喂，易先生，我在上课。喂，我在上课啊。对。好，拍谁。嗯。Okay, so each core basically control 1 pixel, the output of 1 pixel. It will calculate the output of 1 pixel for you. So you have so many pixels on your monitors, right? So that is why, okay, the GPU has many cores. Okay, however, later on, researchers start to find out that, okay, we could use GPU cores to speed up the computation of the matrix manipulations. Okay. What happens? Sorry. Wait. Okay. So let's continue our lecture. Okay. So the simple architecture of McCulloch and Pitts, okay, proposed can deal with logic proposition, but probably not so much useful for the other task. So, you know, there's another proposed simple architecture, okay, by Frank Rosenblatt, okay, in 1957. This is close to the end of the first AI wave. Actually, this architecture was very popular in the first AI wave. And remember I told you, okay, people proved that at that time, like the ANN doesn't work. There's a limitation for ANN architecture, okay. The limitation, okay, they refer to, okay, is this one, is the perceptron, okay, perceptron, okay. So what is perceptron, okay? So this is based on artificial neuron called linear threshold unit, LTU, okay. So the input, output are numbers, okay. So it is no longer just a binary on-off value, okay. Remember in the McCulloch-Pitts model, okay, the neuron can only deal with on-off values, okay. But here, okay, in the LTU, each input connection is associated with a weight. So not only the input is a number, I mean each input is also associated with a weight, okay. So the LTU computes a weighted sum of its input. So assuming we have like n features, we have n features, x1, x2 up to xn, then the weighted sum will be z equal to w1 x1 plus w2 x2 plus blah 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 plus wn xn, or we can write it as w, the transpose of w dot x vector. Okay, of course these two are vectors. I mean, this is like a kind of like a matrix multiplication, okay. So then apply a step function, okay, to that sum and output the result. So what is step function? Okay, this step function, okay, is not specified, okay, so clearly, okay. But if you draw it in a figure, the LTU, or another way to call it is like a, you know, threshold logic unit, okay, threshold logic unit is called TLU. Well, sounds a little bit strange, but LTU and TLU refer to the same thing, okay. So you can see it accepts some inputs, okay, and for each input we have an associated weight, okay, and then after you add up the weighted sum, okay, you apply a step function, okay, and you output it, okay, and the reason, okay, we call it threshold logic unit, okay, why we have that logic there, okay, it is because the step function, the output of the step function mostly will be either 0 or 1, okay. These are the two most popular step functions used with LTU. As you can see, either the Heaviside or a sine function, okay, I mean they output 0, 1 or negative 1, 0 or and positive 1. Okay, pretty much like just the output value are still very, I mean, it's still very binary, right? Very binary, or well, at least the choice is not too many. Okay, the output is not arbitrary value. Okay, just want you to be aware of that. Okay, so to be honest, like the Heaviside is used more often. Okay, so you may ask, well, then if the output is 0 or 1, when you connect them together, like it's still on and off, right? Okay, but remember, we have this weight, right? We have this weight. If it's 0, of course, no matter what way you multiply to, the result is still 0. But if you have if you output 1, after multiply that output with a weight, then the result will be that weight, right? Okay, so it's not exactly just, just binary, okay? So we know single LTU can be used for simple linear binary classification, okay? Because it basically, okay, you can see this function, this one, z equal to this one, obviously, describe a linear function, right? So it can be used for like binary classification, okay? So that's because, well, it's pretty much a linear function, just like kind of like linear regression situation. But linear regression is like you give like a value, it gives you the output value. But when I say this, we use this for classification. I mean like because it describes a linear function, right? So it cut the space into two pieces. So you can treat one piece as like one class, the other half as like the other class, okay? So it can be used for simple linear binary classification, okay? So it computes a linear combination of the inputs, and the result, if the result exceeds a threshold, it outputs the positive class. Otherwise, it's negative. So it's kind of like a linear logistic regression classifier, okay? Or a linear SVN. If you don't know SVN, don't worry about this. Okay, we talk about linear regression. So logistic regression classifier is somehow similar to linear regression. So if you don't know about that, well, don't worry about that too much. But you can certainly check out the first half of the textbook to check out this associated material. But I really have to draw a line, okay? That I refrain from like describing too much about machine learning material, because after all, this class is about deep learning, okay? So if you want to pick up those like stuff, like you can do it yourself, okay? So for example, you can use a single LTU to classify iris flowers, okay, based on the petal length and the width, okay? If you are not familiar with like the English term for flower and 这个是兰花啦 ，OK， you can classify， 你可以分类兰花，那这个 petal 就是那个花瓣嘛 ，OK， based on petal length and width, then you can classify like iris, different iris. We know there are so many iris types. I don't know if you have ever been to like flower exhibitions. Okay, I've been to one. Okay, and there are so many different type of iris out there. Okay, so there are other features. Okay, so we treat the bias feature as like x0 equal to 1. Okay, so we have a weight W0, okay, to multiply with the bias feature, okay, so that we can have a bias term, okay, for our linear, equation. Okay, so this is here. Okay, we include the W0 x0 plus the other stuff, and the W0 x0. That x0 is fixed to be 1. So W0 actually represent the bias. Okay. So yeah, the other stuff like so what is perceptron? Okay, what is its relationship with the LTU? Okay, a perceptron is pretty much a single layer of LTU, okay, with each neuron connected to all the inputs, okay. So these connections, okay, we normally say it's a special pass-through neurons, okay? I mean, for the input, we call them input neurons, okay? So if you draw a figure, it looks like something like this. So these are the input neurons, okay? Whatever it gets input, it just pass through, okay? I mean, sometimes if you are lazy or you really don't need to draw this thing, okay, you just draw x1, x2 here, that's fine. But with this, neuron, you just need to know this is straight pass-through input neurons, okay? And then, okay, you can see the input, including this bias, are fully connected with the single layers of the LTU units, okay? And each LTU will have one output. So this, okay. So a perceptron with 2 inputs and 3 outputs, okay. That is exactly this one, okay. 2 inputs, 3 outputs, okay. So I'm sorry, okay. So I mean in the next slide, okay. So this perceptron can classify instances simultaneously into 3 different binary classes, okay, which make it multi-output classifier. So it can deal with 3 binary classifiers simultaneously, okay. Of course, if you want to only classify one binary, if you want to do one binary classifier, okay, then you don't need so many output. One output will be enough. And for this one, okay, for example, okay, remember I say like there are so many iris flowers, right? Assume the x1 is petal length, the x2 is petal width, okay? Then what happens is that, okay, you can use these 3 outputs, okay, even though each one is a binary, you can use them to represent 8 different classes, okay? Each class is represented by 000, 001, 010, and so on, okay? You can have 8 different classes based on this, okay? So remember I told you, okay, ANN use linear algebra a lot, right? So here you can see we can actually represent the previous perceptron, I mean, into something like this, okay? So in here, okay, the X, okay, represent the matrix of input features, okay? It has 1 row per instances and 1 column per feature, okay? And the weight matrix, okay, is W, okay? So contains all the connected weights except for the ones from bias neuron, okay? So the bias vector B is here, okay? We don't represent bias here, but we put bias here. Okay, any question? Okay, yeah, if you have a question, I mean, feel free to raise your hand, okay? So, and then we have a function, okay, phi, okay? We call that activation function, okay? So obviously, like for different type of neuron, you may have different type of activation function, okay? So, so for TLU or LTU, okay, it's a step function, okay, it's a step function. So you can see that we can deal with like the ANN by using like matrix multiplications. So remember this LTU and perceptron concept was proposed by this Frank Rosenblatt, okay? But the issue is, you know, Yeah, I mean, no, because he introduces this weights for each connection, right? So you have to have a way to determine what value to use for these weights, right? So that's like you know, I mean, Frank Rosenblatt also proposed a training process, okay, to train the perceptron, okay. So this training is based on Hebb's rule, okay, Hebb's rule. This Hebb, okay, Donald Hebb is a biological researcher, okay. Of course, he researched on the biological neuron, okay, and his finding, okay, in his research, he finds that, okay, when a biological neuron, okay, often triggers another neuron, then the connection between these two neurons grows stronger. Okay, remember we talked about like neurons, they may have connections, right? So if these two neurons gets triggered simultaneously all the time, then their connection has positive feedback to increase the connection strength. So the idea was, I mean, summarized in a catchphrase, okay, something like this, okay. Cells that fire together, wire together. Very, very simple catchphrase, okay. So this rule, okay, is known to be Hebb's rule, or we call this as Hebbian learning. Hebbian learning. So this idea is used to train our perception, okay. So what exactly do we use to train the perception? I mean, even if we say, okay, we use this Hebb's rule, but what do we mean by make the connection stronger? Actually, we do it in somehow like in an opposite manner. Okay, so connection weight between two neurons is increased when they have the same output. Okay, so the perception are trained using a variant of this rule. Okay, so it doesn't use this Hebb's rule directly. Okay, so instead, okay, it takes into account the error made by the network. Okay, so if the output is the same as the expected value, okay, then nothing happens. Okay, but if the output is wrong, then we have an error, right? So this error, okay, will reinforce the connection that lead to, you know, it will when I say reinforce the connection that will lead to the wrong output, I mean like it's going to correct the wrong output. Okay, so it actually doesn't enhance the correct input, but it actually correct the wrong output. Okay, so not enhance the connection for the correct output, but for the correct output it doesn't do anything, but for the wrong output it's going to do correction. So let me put it this way. Okay, so it's going to be something like this. This is the weight. Okay, weight. This Wij is the weight. Okay, so this is Xi is your current feature. Is your current feature. Okay, and this current feature. Okay, if this Yj hat is the current output. This Yj represent the ground truth. Okay, if your output is the same as Yj, what happens? These two terms cancel each other, right? Right? Remember, okay, in perceptron, we are talking about binary output, right? because the output is either 0 or 1. Okay, assuming we use heavy side. Okay, assuming we use heavy side. Okay, then, okay, so if this yj hat and the yj, I mean this prediction you get from the current model is the same as the ground truth. These two terms cancel each other, so nothing happens, right? So the previous weight is going to be the next weight, right? Okay, but if the output, okay, is different from the ground truth, okay, then this value multiplied by this feature and this eta is learning rate. Okay, eta is learning rate. Okay, so this will be used to modify this weight, okay, to correct it toward the more correct direction. Okay, so basically, okay, as I said, this is kind of like an opposite of Hebb's rule. Okay, because Hebb's rule tells us that if two things fire together, their connection should grow stronger. But here we don't do this like in a positive manner. If they match, we don't enhance the connection. But if they are the output is the same as as the ground truth, then nothing happens. But if the output is different, we try to correct it. So it's kind of like the other side of the Hebb's rule. Okay. So this perceptron learning rule, okay, or weight update, okay, it can be proved. Okay, it can prove. So the decision boundary of each output neuron is linear. So the perceptron are also linear. Okay, so this perceptron they are incapable of learning complex patterns, as I will show you with an example later. Okay. However, if the training instances are linearly acceptable, okay, then Rosenblatt, okay, proved that this algorithm would converge to a solution. Okay. So what do we mean by linearly acceptable? It means that, okay, we say two sets of points are in a multi-dimensional space are linearly acceptable if they can be completely separated by a hyperplane. Okay, if you have many points, and say two-dimensional, if you have many points, and you can draw a line to break these two set of points into two different half space, then we call this as linearly acceptable. Okay, so obviously, like when your perceptron, okay, training is done, that linear equation represented by this perceptron is going to be similar to that line that separate those points. Okay, and the proof, here is like let's show you like what happens. Okay, so when the output is, if y is plus 1, here we are assuming, the output is, we are using like what should I say, like the sign, okay, sign function. So we have positive 1 and negative 1. But if you use if you use like a binary, okay, like a heavy side, okay, then it's going to be 1 and 0, okay. But anyway, if it's positive 1, okay, and the result, okay, ground truth is 0, then what happens is that the new weight is going to be 1 plus x. Of course, we assume eta, the learning rate is 1. Okay, so what happens if this is w, this is x, this is the new w plus y x. Okay, this is the new weight. But if y is -1, okay, what happens that if w is this one, x is this one, I mean, this is what you have, okay? I mean, visually, okay, this is the, the perception learning or perception training, okay? And this is the algorithm, okay, for perception training. And here is another version to tell you, to say like what the perception learning algorithm is. Or, okay, it is abbreviated as a PLA. Of course, the PLA may represent different meaning. Okay, here we just mean it's a perception learning algorithm, not the other way. Okay, well, if you know what I mean. Okay, anyway, so the PLA can be proved. Okay, assume there exists some parameter vector theta star. Okay, such that theta star, the norm of that is 1, and some gamma greater than 0, such that, okay, we have this. In other words, okay, they are linearly acceptable, okay, because this theta star is like the weights. So weights, the inner product xt is like this is the represent the linear function, okay. Assuming addition that for all t equal to 1 and this one is small equal to r, then the perception algorithm makes at most this many errors. Okay, we can prove that. I mean, this many errors just means like with this many iterations, we are guaranteed that the perception will converge to a correct classifier that separate these instances. So this we have like due to the time constraint, we don't have the time to talk about the proof. Okay, there are the formal proof. Okay, can be found here. Okay, you guys are more than welcome to check it out. Okay, so scikit-learn provide perception class, okay, which can implement a single LTU network. Okay, so it can be used just like you expect. Okay, so you can use it for the iris data set. Okay, so here, okay, you can see we load the iris data set. Okay, here, and here we have like this 2, 3 just means that we want only the second and the third features from this data set, okay, which represent petal length and petal width, okay, and the iris target is basically it's like just show you like what type of iris it is, okay, which is like there's a iris called setosa. Okay, this is one type of iris. Okay, so we want to use this model to tell, okay, if iris belongs to this type or not. Okay, and eventually, okay, we can start from a random state and we fit the training data set, and we are able to do the prediction pretty much. I mean, for a given set of like features, okay, the width and length and width of the petal. Okay, so we are able to tell if this is setosa or not. Okay, so this is like an example of to use the perceptual. Okay, so there's another way to you can also use SGD classifier, okay, to simulate the perceptron class. Okay, so so here, okay, it's equivalent to use a SGD class with the following hyperparameters. So loss equal to perceptron, learning rate, okay, equal to constant, and the eta 0 equal to 1. This is the learning rate. Okay, you could use like a different value if you want, and penalty equal to none. Okay, no regularization. Of course, if you want to include regularization, I mean, you could do that. But perceptron, for perceptron model, it doesn't have so many parameters. So really, I don't think you need to use regularization. Okay, so and this comment is to compare with the logistic regression classifier. If you have no knowledge about logistic regression classifier, don't worry about it. Okay. So remember I said the perceptron was proposed in 1957, okay, and in the late 1969, okay, Marvin Minsky, this guy is a researcher from MIT, okay, Seymour Papert, I'm not that familiar with him, but Marvin Minsky is a very famous guy. He later on, if I remember correctly, he later on went to Stanford, okay, I forgot Stanford or Carnegie Mellon, but this guy is a famous, I mean, he actually got the Turing Award, okay, for his contribution to artificial intelligence, okay. So they highlighted in their paper perceptrons, okay, a number of weaknesses of perceptrons, okay. In particular, okay, the fact that they are incapable of solving trivial problems. For example, they give an exclusive OR classification problem. So this is a very, very simple one. Okay, let me show you. Okay, we have 4 instances. Okay, sorry, 4 instances that belong to 2 classes. So this is a binary classification. Okay, so binary classification. It's binary classification, so that's why. I mean, it can be used. Supposedly, we can use perceptron to handle it. Okay, but unfortunately, you can see that we have 2 triangles and 2 solid squares, and obviously, you can see that the arrangement of these 4 instances, okay, you have no way to separate them by one linear function, right? Okay, because they are somewhat like tangled together, right? Tangled to each other. Okay, so this is at location 0, 0. Or you can say the first attribute is 0, the second attribute is 0. This one is 1, 0. This one is 1, 1. This one is 0, 1. Okay, and then okay, because these 4 instances, as I say, there's no linear model that can separate these 4 instances. Okay, and the perceptron by default is a linear model. Okay, so unfortunately, there's no way for perceptron model, I mean, to deal with this. Okay, but we can extend the perceptron a little bit, okay, and we are able to solve it, okay, something like this. Originally, perceptron, okay, when we say perceptron, we always refer to one layer of LTU, right? Only one layer, okay. But if you try to, I mean, and that one layer cannot solve this. But if we try to use 2 layers, in this example, we have 2 layers, then you will find out that we are able to solve it. Okay, let's take let's try it. Okay, for example, 0, 0. If x1 is 0, y x2 is 0, what happens? okay, the weight, okay, this is plus 1, this is plus 1, okay. So we have, let's look at this. So we have 0 for x1, x2, and we have minus 1.5. So after step function is negative 1, right? Negative 1. So negative 1 with the weight negative 1, it's going to be 1. Okay, 1, okay, here. And how about this? This one is, we have get 0 from x1, x2, but we have negative 0.5 from the bias. So we have negative 0.5. So the result is negative 1. Negative 1 with the weight plus 1 is negative 1. So we have, this is positive 1, right? We got negative 1 here, multiply weight negative 1. So it's 1. 1 and the negative 1. So they cancel each other. So we have negative 0.5 from the second bias. So the result is negative 1, right? Okay, so negative 1 represent this square, solid square class. Okay? And you can try 1, 1. You are going to end up with negative 1, 2. Okay, let's try. So this is, well, 1, 1. Okay, so it's going to be 2 and negative 1.5. So what we got is 0.5, right? So we have positive 1. So we have 1, 1, and the negative 0.5. So again, it's positive 1. So positive 1, negative 1 multiplied by the negative 1, that is, we have negative 1. 1 multiplied by positive 1, we have positive 1. So these two cancel each other again. So we have this, we got this negative 0.5. So the result is negative 1, 2, right? So how about the other two? Let's try one of them. Okay, let's just try one of them. Okay, this one, 1, 0, 1, 0. This is 1. This is 0. Okay, 1. So it's a 1. And the negative 1.5. So we have a negative 0.5. So it's negative 1. Okay, and these two, we have 1 and negative 0.5. So we have 2 minus 0.5. So it's a 1.5. So we have 1 here. Okay. Wait. What do we have? This is like, we have 2, we have 0.5. So it's 1. So 2, yeah, this is also 1. Did I make a mistake? Oh, sorry, this is 0. What did I say? Okay, 1, 0. So this is like a negative 1. And 1, 0. So it's a 1. So it's a 0.5. So it's a 1. So this is negative 1. This is 1. So multiply by the weight. So we get, this is 1. This is 1. So we got 2. 2 negative 0.5. So it's going to be 1.5. So the result is 1. Okay, so this result is 1. Okay, so this one you can try it. The result is also 1. Okay. So the two classes, okay, they are, each one, the solid square is negative 1. The shallow triangle, the class is is 1. And the two layers of perceptron, okay, well, if you call it perceptron, okay, can easily solve this problem. I want to emphasize, this is not the only weight arrangement to solve this problem. Okay, there are many weight arrangements that you can use 2 layers of perceptron, 2 layers of LTU, okay, LTU units to solve the exclusive OR classification problem. Okay, but the issue is, okay, for this, because this is no longer a perceptron. For the perceptron, you are dealing with only one layer of LTU, right? And you can use Hebb's rule to train the model to get the weight, the desirable weight. But if you have multiple layers of LTU, there's no adequate way to train the model. Okay, even though we can specify the numbers to say, oh, this can solve this classification, but we don't have a systematic way to train the model to get those numbers. Okay, at least at the time, okay, when Marvin Minsky, wrote that paper, people don't know how to train this. They only know, okay, this one can do the classification, but there's no a good way to train the model at that time. Okay. So, okay, this resulting ANN, okay, with multiple, LTU layers is called multi-layer perceptron, or MLP. Okay, this is, remember, if you already check out the first project, you will see that I especially ask you guys to use MLP to solve that problem. But of course, I mean, we haven't really. No, we just show you. Okay, if you have more than one layer of LTU, it is called MLP. But in reality, MLP is still slightly different from this. Okay, because we no longer use LTU unit that often anymore, because that one is a little bit too naive. Okay, but anyway, you can see that. Okay, yeah, I mean, we can solve a slightly more complicated problem by using multiple layer perceptron. Okay, so now we are in a position to formally introduce what the multi-layer perceptron is. Okay, and this is perhaps the first one we can call it deep neural networks. Okay, some people say, okay, if your neural network has more than one hidden layer, then we call it deep neural network. But really, like nowadays, the distinction between deep learning and the neural network is really not that much. Okay, you can pretty much use deep learning on any neural network. It doesn't necessarily need to be multi-layers. Okay, I mean, so don't worry about. I mean, when I say like deep neural, if two or more hidden layers, it's called a deep neural network. Okay, but we just say all these belongs to deep learning. Okay, so you can see in this the multi-layer perceptron, we have input layer, we have one output layer. In between them, we have hidden layers. We could have more than one layer in between. Okay, and for each layer, except the output layer, we have bias. We have bias. And the in-between layers, the connection is fully connected. It's fully connected. Okay, this is like when we say MLP, this is like the MLP that we are referring to. But here, okay, as for each neuron, what exactly do we use for each neuron? I mean, we actually no longer use MLT that much. Okay, but we are going to talk about that. I mean, in a minute. Okay, so we also call this type of network as a feed-forward neural network. Okay, what do we mean by feed-forward? Okay, basically the input, we get input from here, and the input gets test. I mean, to go up and up, a layer by a layer, until we get output. So the direction of the data flow is one direction from the bottom to the top. Okay, and we call that feed-forward neural network. Okay. So when there are other architecture, okay, that may not be feed-forward. Okay. For example, in the future, when we talk about recurrent neural network, it's not feed-forward. Okay. But yeah, a lot of ANN are feed-forward, not just multi-layer perceptual. Okay. For example, most of the CNN are feed-forward too. Okay. So when an ANN contains a deep stack of hidden layers, we call it deep neural network. Okay. The field of deep learning studies DNN and more generally models containing deep stack of computation. Okay. But as I say, when we say deep learning, okay, nowadays, okay, it's basically just a research on neural networks. Okay, I mean, to be honest, nobody use one layer to do anything anyway nowadays. Okay, because one layer is just too simple to deal with any meaningful task. Okay, so even so, many people talk about deep learning whenever neural networks are involved, as I said, even the shallow ones. Okay. So, well, yeah, I don't think we have time to finish this. So let's stop here. Okay, we will talk about how we can train the MLP next time. Okay, the training of MLP actually is different from Rosenblatt's I mean the HAPS learning. It's a much more complicated process. Okay, so we are going to talk about this next time. Okay, any question? Okay, when I say I will talk about this next time, I mean in next online class. Okay, next week we don't have class, and the week after next the class will be held online. Okay, just want to remind you guys again. Okay. So, any question? If no additional question, thank you for coming. Okay. 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 So it's already 1 o'clock, so let's get started. Yeah. Today is probably the only occasion that we are going to teach the class online. Okay. The reason is because the school require I mean, when we come back from foreign country,
we need to go through like a 3+4 quarantine, right? So normally like after 3 days quarantine, I mean we are supposed to be able to teach like the class in person, but the school recently tightened the regulations, saying like for the whole 3+4 period, okay, we are not able to, we shouldn't come to shouldn't come to school, okay, and yeah, it happens that I called a code in Vienna, okay, so so you will hear that I cough like a lot, like I mean in today's lecture, but don't worry, because I'm pretty sure it's not COVID, okay, because I had like 2 rapid tests, like and both results turned out to be negative, okay, so yeah, it's I'm pretty sure like next week, okay, we will resume like um the regular teaching in the classroom, okay, you know, so just so this week, okay, this online teaching will be only like just one time thing, okay, so sorry about that, okay. so so last time, okay, we talked about perceptron, and we also talked about the multi-layer perceptron, okay, but the issue about the multi-layer perceptron, okay, the idea of multi-layer perceptron was actually, I mean, proposed like at the end of the first AI wave, okay, but at that time people do not know how to train the MLP, okay, so it wasn't until like 1986, okay, uh, you know, the second wave of the AI, okay, that like researchers found out like you know, there's a researcher called like, his name is D.E. Lumenhardt, okay, um, he has a, you know, groundbreaking paper published in 1986, okay, uh, he proposed the idea of the backpropagation. Okay, so this backpropagation training, okay, allows us to train the MLP. Okay, and in the backpropagation training process, okay, the idea of the gradient descent was firstly used to you know, to train the model, okay, with what is called reverse mode autodiff, okay. um you may not know what reverse mode autodiff is, okay, I will talk about that, okay, later, okay. That's one technique, okay, one technique to um to you know, to compute the uh differentiation, because obviously like during training you need to, you know, when you use gradient descent, I mean, you, by now you should have like a little bit of idea what the gradient descent is, right? So during every iteration you need to identify the gradient, right? You need to compute the gradient. So the the you know, ability to compute the gradient efficiently, okay, is very important during the training process, okay. But I will get to that point later, okay. So basically, what is this backpropagation? Okay, so the backpropagation process is done like this, okay. So for each training instance, okay, the algorithm will feed the instance to the network and it computes the output of every neuron in each consecutive layer, okay. So basically this process is just like, you know, doing the inference, okay, but it's just like you need to record like a state of every neurons pretty much, okay. And that's the first step, okay. And obviously, because as I said, this is the inference, right? So you will have the output, right? So in the second step, okay, we are going to measure, okay, remember we are doing this, but I mean, in a supervised learning process, okay? What we call supervised learning is basically like we, for especially for the training instances, we already know the real answer, okay? So once you use like this network to do the inference, okay, the output you obtained, okay, will be able to be compared with the correct answer, okay? So you will be able to estimate like how much error, okay, is contributed from each neuron in the, in the output layer, in the previous hidden layers, pretty much like you can backtrack the error that is contributed by each neuron in the network, okay? And this process, okay, is where the back propagation gets its name, because from the output, obviously you can measure like the distance between the output and the real answer and the correct answer, right? But you will have to propagate those error, okay, back to every neuron, in each layer, like in a backward fashion, okay. So that's why it's called back propagation, okay. So once you obtain like how much each neuron contribute to this error, okay, in the second step. In the third step is that you are going to, it's a basically gradient descent, okay. You use that to decide like how you tweak the weight for each neuron, okay, to reduce the error, okay, to reduce the error for the inference, okay. So to summarize, okay, if we want to use like short phrases to capture the idea of these three steps, okay, the first one is going to be forward pass, okay. It's just like an inference, right? You have some instances and you know the answer of those instances, okay. So you use the forward pass, okay, to obtain like the state of every neuron as well as the output. And the second step is called reverse pass, okay. Basically you measure the error, the distance, okay. Each neuron contribute to the error, okay. So as I said, this is actually where backpropagation happens, okay. And the third step is the gradient descent, okay. You tweak the network accordingly, okay, so that you reduce the error, okay. So and keep in mind, like because it's a gradient descent, so this is it's going to be a loop, okay. Just like the gradient descent that we discussed like earlier, okay. We actually have to run it like repeatedly, okay, until the error is reduced to a acceptable range, okay. So at that time, okay, we are we believe the network is able to help us to deal with the task that we wanted to do, okay. So this is like how the MLP is trained, okay. So before training, okay, when you have a network, you want to train the network, okay. Remember, I mean, there are so many parameters, okay, for a network, okay. Well, basically, what I'm talking about is are the weights, okay. Um, that includes like the weights for every connection as well as the weights for the bias, okay. So all these weights, okay, it is very important, okay, before training, we initialize all these connection weights in the hidden layers randomly, okay. Remember, like in the gradient descent, we have like a random initialization. Okay, this is exactly just like that, just like that. But you know, in the random initialization that we talk about in the gradient descent, okay, you may feel like, well, if we start from like the case where all the weights are 0, it looks to us that it is still okay, right? But in MLP, if you assign all these weights to be 0, okay, we have some problem. Okay, why? Because all the neurons in a given layer will be pretty much identical, right? Because they have the same weights, okay? And the backpropagation will affect them, okay, exactly the same manner, okay? So this, you know, in some sense, okay, I mean, because backpropagation, I mean, affect each layer the same way. So they will basically, I mean, remain to be the same. So the whole network, okay, is reduced to, you know, to a much simple architecture. Okay, the whole layer, you know, will be reduced just like a one neuron. Okay, you lost like the diversity of your network. Okay, so this is something you want to avoid. Okay, you want to break that symmetry. Okay, so that's the reason. Okay, we want those connection weights to be initialized randomly. Okay, but okay, even when I say we want them to initialize randomly, there are some consideration for this randomization, for this randomness. Okay, so there are actually different random initialization schemes for this connection weights. Okay, I will get to that point. Okay, in the next chapter. Okay, in the next chapter. Remember, I mentioned about like the third wave of AI. Okay, you know, they are you know, some researchers, okay, propose some small tricks that allow the training of the neural network to be much more effectively. Okay, you know, some of those random initialization schemes, okay, are, you know, what I mean, part of these small tricks, okay, that actually help you to train the model much easier. Okay, but we'll talk about that, I mean, in the next chapter. Okay, so another important change, okay, they found out, okay, when they proposed this backpropagation, is that, okay, remember the previously when the MLP, the multi-layer perceptron was proposed, okay, it is based on the idea of perceptron, right? And the perceptron, remember the activation function is step function, right? So the step function, I mean, well, it works well for the perceptron, but for the multi-layer perceptron, especially when you use the backpropagation to train the model, okay, using the step function has some issue. Why? Okay, think about that. Okay, let's go back. Okay, to look at this backpropagation training process again. Okay, the third step of this backpropagation loop is gradient descent, right? So it is very important that, you know, you have some gradient. You have some gradient, I mean, or let me put it in another way, like a slope, right? I mean, if you forget most of your, you know, college calculus, at least you remember slope from your high school math, right? So it is very crucial that you have either positive or negative slope, so that like I mean, you can move the current location to another supposedly better position, right? Okay, but remember the step function that we talked about. Okay, step function. Where is the step function? Yeah, this step function. I mean, if you draw the figure, okay, you will see obviously, okay, it is, you know, no matter where you compute the value, okay, it's going to give you, you know, the gradient is going to be 0, okay, the slope is going to be 0, okay, so that's the issue with this you know, step function, activation functions, okay, so um as a result, okay, they proposed, okay, to use a different activation function. Okay, there are three activation functions they propose to use. Okay, the first one is logistic. Okay, the second one is hypertangent. Okay, yeah, their definitions are given there. Okay, but I believe that you guys at least heard of these names, logistic, hypertension, even though you probably don't use them very often. Okay. The third one probably is a new thing for you. Okay. But it is actually the easiest function. Okay. Which is called rectified linear unit function. Okay. Or abbreviated as a ReLU. Okay. ReLU. Okay. The ReLU basically like when the input is positive, you'll return positive value. When the input is negative, okay, well, it will just give you a 0. Okay, so these three functions obviously are nonlinear. Okay, um, because they are nonlinear, so they are able to, you know, when they combine with like a, remember like each neuron has this step function, which has this activation function, right? So when all these neurons, you know, combined together, okay, they are able to deal with complicated complicated scenarios, okay, and also, I mean, all these step functions that are, these three step functions, they have like a gradient, okay. They may not have gradient all the places, but most of the places they have gradient, so that allows the gradient descent to work its way, okay, toward the optimal, okay. So so here, okay, are the figures that show you the, you know, these three, well, actually four, okay, four different activation function. The red line, okay, on the left hand side, okay, the red line indicates the step function, which, as I said, okay, it works for the perception, but it's not good for the MLP because we are going to use gradient descent to train the model. Okay, and the second one is logit. The logit is pretty much a logistic function. Okay, so you can see the dotted line is a logit one. Okay, it's like this from here to, you know, so it is bounded. Its y value is bounded between 0 to 1. Okay, from 0 to 1. Okay, and third one is the solid blue line, okay, is a hypertangent, okay. It is also bounded, okay. Its y range is also bounded by -1 to +1. Okay, that's the hypertangent. The last one is ReLU. Okay, ReLU is a very interesting algorithm. Sorry, the interesting function. So when the input is lower than 0, okay, it will just output 0. Okay, so it's flat. Okay, when x value is lower than 0. Okay, but when when x value is greater than 0, it is pretty much y equal to x. Okay, it's pretty much a line. Okay, straight line. Okay, and their gradient, or you can say their derivatives. Okay, first order derivatives. Okay, are shown on the right hand side. As you can see, the step function is pretty much flat to be 0. So that's this why, okay, it is bad for gradient descent. You just have no gradient to work with, okay? But for the other three logistic, hypertangent, ReLU, okay, at least we have some gradient to work with, okay? And the one thing you may feel strange is that ReLU, okay, when the input is less than is smaller than 0, okay, its gradient is also 0. Okay, but of course when the input is greater than 1, okay, so greater than 0, the gradient is pretty much 1, right? The just a slope of the line y equal to x, right? So so you may wonder in the ReLU must, it doesn't look like it's going to work very well, okay, in the multi-layer perceptron, but the result is actually very interesting, okay. Well, the logistic and the hypertangent, okay, and the ReLU, okay, for these three explanation functions, at the end, it turns out that ReLU has been adopted like much, the most, okay. It's because like ReLU normally performs much better than all the other activation functions, okay. This may be slightly against the intuition, okay. It is really because like most of the time you will see that, okay, the output is normally not necessarily smaller than 0, okay. I mean, remember like for a neuron, okay, it's going to get like input from for the for a neuron in a hidden layer, okay, it is going to get like the input from all the neurons from the lower hidden layers, right? So what happens is that, okay, even though, okay, at some point of time, okay, its value may be negative, but most of the time, okay, its value is actually not that bad, okay. In other words, I mean, it received like it has like or let's put it this way, okay, it has like statistically speaking, like 50% of the chance for a neuron to have positive value, right? So for a neuron to have 50% of chance to get the gradient, it's already good enough for model training, okay. Well, we'll get to that, I mean, at a later point of the discussion, okay? So these three activation functions, keep in mind, I mean, have been very important, okay, after MLP training has been proposed, okay? So the MLP, okay, can be used for different types of task, okay? The first task, I mean, first type of task is regression, Okay, what is regression? Basically, the regression is that you use a model to predict a single value. Okay, for example, such as the price of a house. Okay, when you are given a certain number of features. Okay, or okay, you predict like um, the stock market, like you know, um, what's that? In Chinese we call it 指数, but I forgot the English term for that. Okay, I mean for a stock market, normally you have a number to indicate like the current situation of the market, right? You can use the MLP to predict that number as well. Okay, uh, of course for a given number of features as well. Okay, so you can obviously also model that as a regression task. Okay, so in that case, your MLP will have a single output neuron. Okay, and its output is the predictive value. Okay, and you can also do what we call multivariate regression. Okay, what is multivariate regression? Okay, I believe you have seen some model that is able to predict like the to do like object detection, right? To do object detection. In the object detection model, it not only identify the type of the object, it also, give you a window, to bound to that window can, is a bounding box for the object. Okay, so in the picture, so this is like what the object detection model is. Okay, I will actually, we are going to talk about object detection model like uh, at the end of like well, next chapter. Okay, so so think about this. Okay, when you want to output a bounding box for object, okay, you do need to have, for example, the center location of that object, as well as the width and the height of that bounding box, right? So for each bounding box, actually you need the center coordinate, as well as like the width and height of that bounding box. So there are totally 4 numbers that are required, okay, for one bounding box. Okay, so you need to output 4 numbers. Okay, 4 numbers here. Okay, I mean in the description of the slide, I mean if you want to output like a coordinate, okay, just coordinate, I mean in this case it's like a center of the object, then just x and y value, right? But if you want to have like the bounding box, then you need the size of the window, so there will be width and height. So for these 4 outputs, they are all numbers, and we call such a task as a multivariate regression. So depending on how many numbers you want to output, you will have to have like 1 neuron for each number. Okay, that's for the output layer, of course. Okay, so so when building a MLP for regression, okay, you do not want to use any activation function for the output neuron. Okay, so in that case, the output can be any value. Okay, positive, negative value, pretty much anything. Okay, but in certain application, okay, you want to, it is a regression task because well, you want to output number, but the number you want to output, okay, may always be positive. Okay, for example, like remember like the object detection example that we talked about. Okay, no matter it's like the x and y coordinate as well as the width and height of the bounding box. Okay, all these four numbers are pretty much positive, right? And in the worst case, I mean, it can be zero, but that's pretty, they must be greater or equal to zero anyway, right? So in that case, okay, you could use a reload activation function in the output layer, okay, for this to output these numbers, because reload, as you know, like its output is going to be greater or equal to zero, okay. And another possibility, okay, other than reload, is the soft plus activation function. Okay, its its definition is given here. Okay, it's a log of 1 plus expz. So you can see that, okay, when z, okay, is negative, okay, the exponential of a negative value, okay, is going to be, very close to zero, right? So log of 1 is going to be close to zero, right? Close to zero. Remember, this expz is going to be, well, it's going to be 0 point something, right? It's still going to be positive. Okay, so it's going to be 1 point something. So log of 1 point something is going to be close to zero, okay, when z is negative. Okay, when z is positive, or when z is zero, it's going to be log 2. Okay, log 2 will, depending on what your base is, okay, if it's like a natural number, then if it's e, okay, then, well, it's going to be smaller than 1, but somewhere between 0 and 1, okay. And when the z is positive, okay, then, the log 1 plus expz is going to be close to z. Okay, so this soft plus function, okay, um, is close to 0 when z is negative and close to z when z is positive. So in some sense, the shape will be similar to ReLU. Similar, I'm not saying the same, okay, but it's going to be, what should I say, smoother than ReLU. Okay, so and obviously because the output is guaranteed to be greater or equal to 0, so it can also be used as the activation function of the output neuron. Okay, in case if you are looking for you know the result to be greater or equal to 0. Okay, and if you want to guarantee the prediction, okay, will fall in within a certain range, okay, then you may use either logistic or hyperbolic tangent, hypertangent, because logistic, we know the range is between 0 to 1, right? For hyperbolic tangent, okay, hypertangent, the range is between -1 to +1. So, in case if that's not what you want, okay, that's not the range that you are looking for, you can scale it, okay, you can scale it to fit the range that you are looking for, okay. Even if scaling doesn't do the job well, okay, you can even do like shifting, okay, but basically like you could use like this like hypertension or logistic, okay, for in the case if you're looking for like a you know if you are looking for like a number that is within certain range, okay. So okay, for regression task, okay, the loss function can be, can be a mean square error, okay, as we have already seen in the previous discussion, okay. But if you have a lot of outliers, the mean square error, okay, may not work well, okay, because it will put too much emphasis on the outliers, okay. So in that case, you could use mean absolute value, mean absolute error, okay, to replace the mean square error, okay. Alternatively, you can also use Huber loss, okay. The Huber loss is kind of like a combination of mean square and the mean absolute error, okay. So um, um, the Huber loss is quadratic when the error is small and is linear when the error is large, okay. So it allows you to deal with the outlier much more effectively than the mean square error. But at the same time, because mean square error has the advantage of like a quick convergence, so the Huber loss, okay, also enjoy that quick convergence advantage, okay. So Huber loss is one, loss function you could consider, okay, in case if you have quite a lot of outliers in your training set, okay, in your training set. So here's typical regression MLP architecture I listed in this table, okay. This is just a reference for you, like in case you want to create an MLP for regression task, okay. So this is like a, just like a reference. I'm not saying, you have to have the exactly same MLP architecture like what we have in this table, okay. But this table serves as a good starting point, okay, especially, okay, before you try anything else, okay. So as you can see, like one thing I want to point out, okay, for the elevation function in the hidden layers, okay, you can see we prefer ReLU, or and you may ask, what is CRU? Okay, we are going to talk about CRU later, okay, probably not now, okay. So guess that's about it. So okay, so obviously, okay, the MLP can also I'm sorry, can also be used to deal with classification. Okay. For classification, there are actually different type of classifications. The first one is what we call binary classification. Okay. For example, like you want to classify, okay, either true or false for a certain event. Okay. Um, um, if these true and false, they are, what should I say, like exclusive. Okay. For example, like the sex of a human. Okay, it could be male or female. Okay. Uh, well, I know, like some people may say like there are some transsexual, sex like option nowadays. Okay, but let's consider this problem more classical. Okay, classic. Okay, then we only have male and female. Okay, so things like the task like this, okay, will be what we call binary classification problem. Okay, so so if it's a binary classification problem, we normally have a single output neuron, and we use logistic activation function. Okay, remember, logistic activation function will output a value between 0 to 1, right? So that value, that output value will be represent will be will represent the probability, okay, probability of a positive class. Okay, so for example, okay, remember I say like the sex, you may want to use certain, you know, attribute or to predict a person is male or female, right? Okay, so so let's consider the positive class to be male and negative class to be female. Then if you get like a 0.7 output, that means this person is 70%, okay, likely to be male, okay, and obviously it's going to be 1 minus 0.7, which is like a 30% chance to be a female, okay. So this is the binary classification problem, okay. And we also have like a multi-labeled binary classification task. What is multi-label binary classification task? Sometimes, I mean, there are some problems, okay, that has like a more than one binary classification, okay, but this, you know, multiple binary classifications, I mean, they may not be, what should I say, like, they may have certain correlation, but at least they are not disjoint, or they are not. For example, okay, let me give you an example that's probably easier. Okay, for you, for for example, sometimes we want to design an email spam filter, right? Spam email filter. Okay, so we want to classify if the incoming email is ham or spam. Okay, ham means it's harmless. It's a regular email. Spam means this email is it's harmful, or it's like it's maybe it's a phishing. Okay, he try to do some bad thing to your computer. Okay, and we sometimes also want, at the same time, want to predict, okay, if this email is an urgent email or non-urgent email. Okay, but so obviously, to classify an email is ham or spam, it's a binary classification, and to predict an email is urgent or non-urgent, it's another binary classification, right? But for these two binary classifications, they are not necessary, because an urgent email, okay, can be, if you look at these two binary classifications, okay, a ham email, okay, can be either urgent or non-urgent. Okay, you may get a email from your friend, okay, I mean, just for chatting, okay, so obviously it's not urgent. But you may get an email from your advisor, I mean, who wants you to report to him immediately. Okay, this is obviously an urgent email, right? So, but both emails are ham, right? But for spam, most likely the spam email, well, obviously it's going to be non-urgent, right? I mean, you don't have a spam email that's urgent. That sounds a little bit strange, right? Okay, but you can see that there are certain correlation between these two binary classification, but they are not exactly, what should I say, I mean, the output, you can sort of treat these two binary classification as two independent independent tasks. Okay, sort of. even though they are sort of correlated a little bit. Okay, so in that case, you just have like a two output neurons. One for each binary classification, and of course, I mean, just like the single binary classification, you still use like a logistic activation function here. Okay, and that should normally do the job well. Okay, so for classification, there's also another thing called multi-class classification, which probably is the most common classification task you will see. Okay, so in this case, each instance can belong to only a single class. Okay, out of several possible classes. Okay, for example, like one of the famous tasks is that you have some digital like a writing writing digit image. Okay, and we want to identify if this digit is it can only be 0 to 9, right? One of these 10 classes. Okay, so obviously that image, for a given image, it can only belong to one class, right? We call that as multi-class classification. Okay, so in that case, okay, we normally have one output neuron per class. Okay, and then we use softmax activation function for the whole output layer. Okay, so the softmax function will guarantee that all the estimated probability for each class. Okay, let's say like if it's like a written digit image. Okay, as I say, it could be from 0 to 9, right? 10 classes. So because as I say, like we will have one output neuron for each class. So we'll have like 10 output neuron, right? So each output neuron will output the probability for that image belong to that class. And the summation of all this probability will add up to be 1. Okay, so this is like a much natural, okay, situation that we are looking for. Okay, so this is called this type of test is called multi-class classification. So you may wonder like what is a softmax function? Okay, softmax function looks like this. Okay, for each class, let's say class K is going to be theta K to the power of T times X. Okay, and so that's for one class, right? The whole function, okay, is given below. Okay, so you can see that, okay, the because for the PK just means like a probability for the case class. Okay, so it looks like summation. Okay, at the in the denominator and the exp skx in the denominator. So you can see that obviously, okay, if you sum up the probability for all k for all the k classes, the result will be 1. And also like this pk the probability for the k class, okay, this value is guaranteed to be greater than it's between 0 to 1, guaranteed to be between 0 to 1, because the no matter it's numerator or denominator, they are guaranteed to be greater than 1, greater than 0, right? Greater than 0. And the denominator obviously is a bigger value than denominator. Okay. So this is like modern MLP with that, I mean, that is doing like a multi-class classification. And you can see we have like some hidden layers in between. We have like input layer, and in the output layer, okay, we will normally draw a softmax, okay, no, to demonstrate, to pretty much indicate like this is a multi-class classification problem. Okay. So this is like the typical classification MLP architecture. Again, okay, I just want to emphasize that this table is there just for your reference. Okay, it's not necessarily that your MLP model has to be exactly the same as what is listed here, but it serves as a good starting point. Okay, when you design a MLP for a classification task. Okay. And one thing we haven't talked about, okay, the loss function, okay, for classification, we normally use cross entropy. Okay, we will talk about this later, okay, when we talk about the programming, okay? So, well, it's already break, okay? Let's take 10 minutes break. When we come back, we'll continue our discussion, okay? Hello. So, can you guys hear me now? Okay. Okay. I'm sorry. Yeah. So we talk about the biological the neural network is um the inspiration of artificial neural network. Okay. I mean at the beginning of this chapter, right? But um you know when the the biologist okay do certain experiment they found out that the activation function okay implemented in the biological neurons okay is kind of like a sigmoid which is like a s-shape activation function okay um which are kind of like for example the sigmoid the the hypertension and the logistic they are also s-shape okay so actually because of that okay the um the AI researchers okay try very hard to use the sigmoid function okay in the neural network for a long period of time okay because researchers just think like if God use sigmoid okay to create like the 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 human and all these animals there must be a reason right I mean but it turns out that the ReLU activation function okay generally works much better in artificial neural networks okay as I already explained okay ReLU is actually you could probably argue it to be like the most popular most popular activation function okay so this is one of the cases where the biological neural network the biological neural network is was misleading okay or you can probably say this way okay um maybe God is afraid like a human to be too smart. Okay, so he decided not to use like the best architecture to design like animals like brain. Okay, otherwise like maybe we'll be much smarter. Okay, than what we are now. I mean, who knows? Yeah, but anyway, this is like they are as I say like they are the biological neural network now is considered very different from the artificial neural networks. Okay, so this is one major difference. Okay, so remember I told you that in um, in the backpropagation paper, okay, they propose reverse mode autodiff. And I told you that we are going to talk about what this reverse mode autodiff is. Okay, so here we go. Okay, so for that paper, just for you to understand, for that paper, they proposed this idea, but they didn't really implement it. Okay, it actually wasn't implemented until Google create the TensorFlow. Okay, to implement the reverse mode autodiff. Okay, but what reverse mode autodiff is, that's it's basically as I said, you know it's a differentiation technique. Okay, so that's since it's differentiation technique, that's probably it's a good time to talk about like different differentiation techniques. Okay, so suppose you have a function like fxy equal to x squared y plus 2. Okay, and you want to do partial derivatives. Okay, remember, um, um, in our gradient descent, okay, because it's going to be higher dimensional. Okay, to be honest, like in this example, we use only two-dimensional x and y, but in reality, when it's in like a artificial neural networks, okay, the function that we commonly see, okay, it has like so many variables, okay, maybe hundreds of thousands of variables. It's very common, okay, and we want to get the partial derivatives for these functions, okay, in order to perform gradient descent. Okay, so okay, there are 5 different approach we could use, okay, to do differentiation. The first one is manual differentiation. The second one is called symbolic differentiation. The third one is numerical differentiation. The fourth one is forward mode autodiff. The fifth one is reverse mode autodiff. The first 3 are, well, pretty straightforward. Okay, manual differentiation, I think there are 5 rules. I don't think I need to go through all these 5 rules. I mean, you guys, as long as you have taken like college calculus, you know how to do differentiation, right? So for partial differentiation, just remember, you just treat like all the other the variables as constant. Okay, just concentrate on the variable that you are dealing with. For example, if you are doing like partial differentiation for x, then you can treat y as a constant. Okay, that's about it. Okay, so the other part, I mean, are similar to just regular differentiation. So I just so you guys know how to do it, right? So here just to show you like how we do the partial differentiation for the example I just gave you. Okay, for it's very straightforward, so I will not spend much time here. But okay, this approach obviously can become very tedious for more complex functions. Okay, it is called manual differentiation because it takes a human to involve in the differentiation. Okay, and because it's a human's job, so you run the risk of making mistakes. Okay, the good news is that, okay, because we have rules, right? So these rules can be sort of like implemented into by a computer, okay? So which is called like symbolic differentiation. So what symbolic differentiation is like this, okay? So say you have a function gxy equal to 5 plus xy. You first like represent this 5 plus xy in a tree like left-hand side. Okay, and now, okay, if it's a plus sign, okay, you need to do partial derivative for both sides. Okay, so on the left-hand side, okay, from root, because root is a plus, right? So when you do the partial differentiation, because it's like the sum of 2 functions, so basically just try to get like a partial differentiation of both sides. That's it. And the left-hand side is 5. So when you do the partial differentiation on 5, it's 0. On the right-hand side, it's multiplication, right? When it's multiplication, then we change it to be like a plus, and it's going to be like the first one, the first term derivative times the second term. I'm sorry. Plus, okay, I mean, and the other part is the first term times the derivative of a second term. So basically just replace each node with, I mean, using the rule that we just had. So it's very straightforward as well. Okay, so obviously, okay, for a small tree like left-hand side, okay, with this symbolic differentiation technique, okay, even though it's done automatically by the computer, it could be grow into a big tree, okay, very easily, especially if your function has a lot of multiplications, okay. So, but obviously you can also like simplify the tree on the right hand side, okay. I mean, if you can prune it a little bit, for example, like if anything multiplied by 0 is going to be 0, right? So you know that. So for example, like this part is gone, okay. This subtree is gone, okay, because it's a 0 times something, okay. So and if something plus 0, it's going to be just, you can prune this left branch as well. So the result is going to be just a y, okay, very simple y, okay. So, yeah, with a certain, if you implement the pruning technique, it's going to work reasonably okay, okay. So, so this symbolic differentiation technique works fine, but first, it need, I mean, it needs certain simplification. Second, okay, if you try to get like, for example, partial g, partial x, you need the one graph, right? And if you do another partial g, partial y, you'll need to do it again, okay? It's going to come out with another tree structure, and you need to prune it again, okay? So yeah, it takes quite some time, okay, if you have a lot of different variables there, okay. So that's like the issue for this um symbolic differentiation, okay. The third one is the another issue for the symbolic differentiation is that okay, it cannot deal with like a function that is defined by, for example, like a function, a computer program. For example, like this function, my function. Okay, it obviously this function looks strange, a little bit strange, right? But if you try to use symbolic differentiation, it doesn't work. Okay, for function like this, unfortunately. Okay, so another approach is called a numerical differentiation. Like we all know that the differentiation is pretty much can be treated as like something like this, right? I mean, so I mean, you just try to use a very small epsilon, okay, and you are able to compute the differentiation value, okay, at a certain location, of course, okay. So so for example, okay, assume that your function is like um x squared y plus 2, this one, remember we use this one, x squared y plus 2, and then we can use numerical differentiation. Okay, we define fxy first, and then we define the derivative of fxy, okay, and we add this x epsilon, y epsilon, okay, then to be something like this. And then when we want the DFD, partial f, partial x, we just, use a very small value for x epsilon, okay, and the y epsilon to set to be 0. And if you want the partial f, partial y, you just call the derivative f 3, 4, and set the x epsilon to be 0 and y epsilon to be a small small value, and it will compute the partial derivative for the f at the location 3, 4 for you. Okay, so this is obviously a very easy way to compute the partial differentiation. You don't need even symbolic differentiation. Okay, and it works obviously for any way, any function that you define. Okay, by as long as it's computable, right? But the issue with numerical differentiation is that it's not so accurate, right? It can only give you approximation. Okay, the result is supposed to be 24 and 10, but as you can see, after the computation, it gives you these values. Okay, well, it's close to 24 and 10, but it is not exactly the right value, right? So this is the first issue. And then the second issue is that, okay, look at here. When you call this derivative f3 for 0.001 and 0, okay, because it's going to call this derivative, okay, function you defined, right? So basically you are going to compute this f twice, right? And you call the partial f, partial y, you put these numbers there, it's going to call the f again twice. So supposedly, okay, if you have like here, because we have two variable x and y, so to compute the partial x, you call f twice. To compute the partial y, you call the f twice. Okay, if you have like 1,000 variables, okay, the worst case is that you are going to call the function f 2,000 times, right? Of course, I mean, if you observe like very carefully, you will see that, okay, because this fxy is going to be used all the time, right? You can only just compute this once and use it like for different partial derivatives. So yeah, I mean, in that case, if you have 1,000 like variables, then you will call f 1,001 times. Okay, so this this computation is still linear to the number of variables, right? So we still consider this inefficient. Okay, we consider this inefficient. So is there any way that we can, work around with these problems? Okay, so there are, so far, for numerical differentiation, we have two issues. First is inaccurate, right? The second one is like it's not efficient. So let's see if we can first solve the first problem, the inaccurate problem. Oh, the advantage of numerical differentiation. It works for like, it's very simple. And so you can use it as a tool to check like if any method you implement are correct or not. Okay, so this is like an advantage of numerical differentiation. Okay. So now, okay, the next approach is called forward mode auto-diff. What exactly is forward mode auto-diff? Okay. The forward mode auto-diff is not symbolic differentiation, okay? And it's not numerical differentiation, but you could say it's their love child. Okay, they are conceptually has some connection to these two approaches. Okay, so it relies on dual numbers. Okay, dual numbers. So we would write a number as a plus b epsilon. Okay, a plus b epsilon. So a number is represented as a b pair. Okay, where a is a regular number and the b epsilon. Okay, where this epsilon is a very small number. Okay, we consider epsilon to be a very small number. So anything multiplied to epsilon is considered very small. Okay, so it is so small that when this epsilon gets squared, okay, such as epsilon squared, okay, we can just we just consider epsilon squared to be 0. Okay, so conceptually, okay, or like intuitively, you can think of this dual number, for example, 42 plus 24 epsilon, as something like 42.0000 many zeros, and we have 24 at the end. Okay, I'm not saying this is the exact the correct idea, but I'm saying this is a good intuition. Okay, so dual number is represented in memory as a pair of floats. Okay, just AB. Okay, so 24 plus 24, 42 plus 24 epsilon just represented as 42, 24 in the memory. Okay. There are some operations for these dual numbers. When a dual number is multiplied by a lambda, it's going to just to be lambda A plus lambda B epsilon. Okay, and then when two dual number, okay, add up, okay, A plus B epsilon plus C plus D epsilon. It's going to be A plus C plus B plus D epsilon. This is very straightforward, right? And when two dual number multiplied together, it's just like regular multiplication. The only thing that is important is that this term, because it has an epsilon square. Remember, I told you epsilon is so small when we have an epsilon square. This term pretty much vanished. So the result is going to be AC plus AD plus BC epsilon. Okay, so far so good, right? So you may not, up to now, you may have no idea what this dual number, why this dual number can be used to solve the partial differentiation. Okay. Then, okay. Do you know this formula? HA plus B epsilon equal to HA plus B times H prime A times epsilon. This may not be look like so obvious to you. So I will do I how do I open a whiteboard? Okay, let me use a point here. Let's see if I can write. Okay, we know like H. Oh, this look ugly. H prime A. How come it doesn't? Hate it. It doesn't work. Shoot. whiteboard. Oh, here. Okay. We know like can you see the whiteboard? Okay, good. Okay. Let me. Okay. Where is it? This is obvious, right? This is obvious. Okay. H prime A equal to H A plus BE. This E is epsilon. Okay, sorry. I mean, I cannot type like epsilon like easily. Okay, just use E as epsilon. Okay, A plus B epsilon minus HA divided by BE, right? Okay, according to the limit theorem, right? Like the derivative is just like the right hand side, right? Because remember the epsilon is very small value. Okay, then okay, you multiply, you try to put this multiply the denominator to the left hand side. Okay, and then you move the minus HA to the left hand side, and you are going to get this. You are going to get this, right? So this function, this formula is really obtained from the limit theorem. Okay, or the formula we use for the numerical differentiation. Okay, so we know H A plus epsilon. Okay, will give you both HA and the derivative H prime A in just one shot. Okay, this is very interesting. Okay, let's see how it works. Okay, so this is a figure that show you the, remember we have like a x squared y plus 2, right? So this is pretty much the path tree for that function. And then for the x, here, if you want to compute the partial x, okay, you put remember it's you want to compute the location, the partial derivative of at the location 3, 4. So we put the 3 plus epsilon at the location x, and the y to be 4. So this multiplication, well, it's going to give you 9 plus 6 epsilon. Well, plus epsilon squared, but epsilon squared is no, it's gone. Okay, and y is 4, right? So 4 times this we have 36 plus 24 epsilon. And we have y plus 2 here, right? So it's 6 here. And then we have like a multiple, we add up these two to get 42 plus 24 epsilon. So you can see 42 is f34, and 24 is the partial derivative of f over x at the location 34, the exact value. Okay, and if you want to get the partial f partial y at this location, you just put the x to be 3 and the y to be 4 plus epsilon. And you are going to get f34 and the partial f partial y34. No, with one evaluation. So I hope like this is clear to you guys. Okay, so this is cool, right? This idea is called forward mode autodiff. So it pretty much solved the inaccurate problem that we had in the numerical differentiation. Okay. But there's still issue, okay? Because yeah, you don't need like a lot of different trees, okay? Like symbolic differentiation when we evaluate like a different partial derivatives. But regardlessly, okay, for one partial differentiation, we need to pass this tree once. So if we have like if we have 1,000 variables, then we need to go through this tree 1,000 times, right? So this is like still inefficient. Okay, it's still inefficient. So so this is where the reverse mode autodiff shines. Okay, it is like so efficient. It's accurate and efficient. Okay, it can compute all of these values in just 2 passes through the graph. Okay, so this is like the best approach. You really cannot beat this reverse mode autodiff. Okay, so what is reverse mode autodiff? Before I talk about the reverse mode autodiff, I want to tell you, I want to make sure you guys know this formula, right? Partial f partial x equal to partial f partial ni times partial ni partial x. You know this, right? This is called chain rule. I hope you guys, still remember this chain rule from your college calculus. I mean, you probably learn chain rule from not necessarily in the differentiation part, but from like integration. When the teacher, the calculus teacher teach like we taught like a integral. Okay, but nevertheless, okay, the chain rule is chain rule. Okay, it should be reasonably easy. Okay, no matter you understand it from symbolically speaking or like conceptually speaking, it should be very easy to understand. Okay, so then what is reverse mode autodiff? Let's we first give each node a different name. Okay, so you see the x we call it n1, for y we call it n2, For 2, we call it N3. For the X square, this node obviously means it's X times X, it's X squared, right? We call it N4, okay? And then this one is, this node represent X squared Y, we call it N5. For this one, it's Y plus 2, we call it N6. And the root, we call it N7. So far, so good, right? We just try to give a name for different node, okay, for each node, that's it. And after this naming, obviously, N7 is the same as function f, right? Because the root is function f, right? And the N1 is pretty much x. N2 is pretty much y, right? I hope like it's easy to understand. Okay, and then let's have a look. Okay, partial f partial N7 is going to be 1, right? No question about that. Because, well, f is N7, right? So we know that for sure. Okay. And then partial f partial N5. Okay. Partial f partial N5 is, remember, N7 is the N5 plus N6, right? N7 is, I'm sorry, N5 plus N6. So partial f partial N5 is going to be, you know, partial f partial N7 times partial N7 partial N5. Partial f partial N7 is 1, that we already know. And partial N7 partial N5 is 1, right? Because N7 is N5 plus N6, right? So N6 has nothing to do with N5, so it's going to be 1. So 1 times 1 is 1. So far, so good, right? Okay, and let's go down here. Partial f partial N4. Okay, it's going to be partial f partial N5 times partial N5 partial N4. Okay, and the partial f partial N5, we already get it to be 1. So we put it 1 here. Partial N5 partial N4. So, well, N5 is like N4 times N2, right? N4 times N2. N4 times N2, partial N4 is going to be N2, right? So it's going to be 1 times N2. 1 times N2. And we happen to know N2 is Y, right? Which is 4, because we are looking for the value at location 3, 4. So Y is 4. So 1 times N2 is 4. So it's going to be 4. So so last one. Okay, when we go down, partial f partial x actually is partial f partial N1 is partial f partial x equal to what? Equal to N1, okay, times N4 plus N1 times N4. So the result is 24. Okay. Because like, well, it's going to be partial f partial N4 times partial N4 partial N1. Okay, because, and we have two different paths, so we need to add them up. We need to add them up. So that's the, I mean, that's the reason we have this. Okay, we have 2 paths, so we add up these 2 paths, so we get 24. And the other part, the other branch, are pretty much the same. So you get like, you know, you can, with this like, with this naming and the go pass, all this, you get like a partial f partial x and partial f partial y all together. So this is very, very powerful technique. Okay. this one is same. Okay, you get the value from here as well as value from here. You need to add them up. Okay, so this is called reverse mode order diff. It simultaneously give you partial f, partial x, and partial f, partial y, with just a very simple operations. Okay, as long as you know how to utilize the this chain rule. Okay, but so here we talk about like how this second pass works, but I think I already told you about this. So reverse mode order diff is a very powerful and accurate technique, especially when there are many inputs and a few outputs. Okay, this is like always the case for the training in the neural networks. Okay, we have so many input or so many variables, but a few outputs. Okay, the variable can be like thousands of variables, but we only have like a few outputs. The number of output actually depends on your task. Okay, if it's like a regression, it's how many number you want to predict. If it's like a classification, okay, it depends on number of classes, but it's not going to be too many anyway. Okay, and you require only one forward pass plus one reverse pass for output to compute all the partial derivatives for all outputs with regards to all the inputs. And also it can deal with functions defined by arbitrary code. So it can also handle functions that are not entirely differentiable, as long as you are asking for the value at the place where it is like it can be differentiated. Okay, so this is a very powerful technique. But you see that this idea has been proposed in 1980. When was that? This idea was proposed by this paper. Sorry. This paper, 1986. But it wasn't get implemented because it's very difficult to implement. It wasn't get implemented until Google's TensorFlow 1.0. It was implemented by a team led by a very famous software engineer called Jeff Dean. I really suggest you guys to search for this guy's name, Jeff Dean, Jeff Dean. He's very special person. There are many important Google project that was like led by this guy. Okay, you can probably say that. I mean, if Google's current status, is at least I would say more than 30% is due to this guy. Okay, so he's considered, if you remember, like I mean, we used to say like there are several gods, right, in those big companies. Now, one of the gods at Google is this guy, Jeff Dean. He's very young. Okay, I believe he's even younger than me. Okay, he's like I forgot his late 40s or early 50s. Okay, but he's a young guy. Okay, so so if you implement a new type of operation in TensorFlow, okay, and you want to make it compatible with a reverse mode autodiff. Okay, remember, as I said, TensorFlow use the reverse mode autodiff. Okay, then you have to provide a function that is built that build a subgraph to compute its partial derivative with regards to its input. As an example, okay, if you implement a function that computes the square of its input, such as fx equal to x squared, then you need to provide the corresponding derivative function f prime x equal to 2x. That's relatively easy, right? So, I mean, by providing this derivative function, okay, you are the the TensorFlow is able to extend its reverse mode autodiff to include your operation, okay, to work with like any other like operations together, okay. So this function does not compute the numerical result, but instead you build a subgraph that will compute the result. So pretty much like even though we are not going to teach TensorFlow directly, TensorFlow, okay, is really about computer graph, okay, because like it treats the computation as a graph. Okay, so it has its advantage, but also it has its disadvantage because it may not look that straightforward for the first timer, okay, but that's one reason. I mean, TensorFlow is not as popular now, but with like Keras, I mean, as its like function, I mean API, hopefully like TensorFlow 2.0 hide its like detailed implementation at the back end. Okay, so let's well, it's already break time, so let's take 10 minutes break. When we come back, we're going to discuss like Keras a little bit. Okay.
So I finally, I mean, make it back to the, lecture like in class. Okay, so yeah, the first project is actually due this week, right? Today? Okay, yeah. So to be honest, like the first project will use MLP, which we are teaching right now. So to be honest, we are a little bit behind the schedule. The reason is because of my trip to Vienna and I remember we have a holiday, right? Yeah, so those contribute to like a little bit like behind the schedule, but the MLP is relatively easy, so I think like it should be okay. But I'm going to post the second project before next week, okay? So just want you to be aware, okay? Yeah, if you want to get started early, okay, please remember to download and start working on the second project, which is, I mean, well, it will be on CNN, okay, before next week, okay, from the EE class, okay. So anyway, so that's, let's try to get this MLP stuff like over with, okay. So at the end of last lecture, we talked about using Keras to create the the model that recognize the fashion MNIST data set, right? To classify the data set. And to be exact, I mean, we are talking about like the sequential API, okay? So we can, obviously also use the sequential API to create the model for the regression task, okay? I mean, I already explained what, the regression task is, right? So basically you need to predict or you need to regress a number, okay, from this model. So one of the, good example that use the regression MLP is like a California housing problem. Okay, in this data set, you are given like a number of features, okay, such as like locations or like the price of the neighbors, okay, etc. Okay, and then you need to predict like the cost of a house. Okay, so similarly we can load the data set from the scikit-learn, okay, and then we split the data set for the for the test, training and test into training set and test set, and then you just import the standard scalar, which is used for like the data pre-processing, and that's it's pretty much about it. Okay, this part is about like data retrieval and data pre-processing. So I think that those are pretty standard. I mean, we split the data, as I said, into training set, test set, and the validation set, and we use the standard scalar to scale the different features, so that like each feature will have the similar inference to your prediction. Okay, so and then here, okay, we can use the sequential model to create, sequential API to create a regression model, okay? And compared with the fashion MNIST model, this one is, obviously a lot easier, okay? You can see we only have one hidden layer, okay? And then this is actually, the second layer is actually the output layer. Okay, the output layer only has one neuron because we are only predicting one number, okay, which is the price of the house. Okay, and because the price of the house, well, is a positive, right? And it doesn't have a limit, especially if you consider like the house cost, or like in the current market, the house is so expensive, right? So we don't use any activation function there. Okay, remember like we talk about like a number of consideration when you create a regression model. Okay, if you're of course, like since the house price is positive, you can also consider using the ReLU activation for your output layer. Okay, but of course, if you don't want to use that should be fine. Okay, and you can see this is much easier model, as I said, than the fashion MNIST one. And then we compile the model. Okay. We use mean square error, okay, as a loss function, okay, SGD, and then we train the model, okay, pretty much for 20 epoch, and that's it, okay. And then with the trained model, you can do the, you can evaluate it, and you can even use the trained model to do certain predictions. That's pretty straightforward, okay. So, so pretty much, okay, we show you what happens? I show you like how to use a sequential API to create a classification model and a regression model. Okay, but the sequential API is good only for what we call like a simple model, in the sense that the model is only like a feed forward. Okay, you only have one data, one path for the data processing, okay, in the model, okay. If that's the case, sequential API work pretty well, okay. But if you want to create a more complicated model, for example, okay, sometimes you want, you may have like the data that need to go through the model with more than one path, okay? Or sometimes you may want your model to be able to to deal with more than one input, okay? Or even more than one output. You may wonder like in what situation do we need like the model that deal with more than one input? When I say more than one input, I'm not saying like more than one feature. Of course, like sequential data is able to do that. Okay, I'm talking about like you have two sets of inputs. One set goes through one path. The other set of input that goes through the other path. Okay, and for this type of like a more complicated model, okay, the Keras provide the functional API to deal with that. Okay, so what is functional API? Okay, it's again, the best that we just show how how it is used to create a model by means of an example. Okay, here we are trying to introduce a model. Okay, which is called wide and deep. Okay. Wide and deep neural network model. Okay, so this model actually was created by Dr. Heng Zhizhen. Okay, just by looking this name, you feel like a very close to you guys, right? Because yes, this guy is from Taiwan. Okay, and I believe he got his PhD from Carnegie Mellon, and he's now working for Google, if I remember correctly. Okay, so this guy made some very important contribution to the recent advancement of the deep learning. Okay, one of the important concepts he proposed is this wide and deep. Of course, this wide and deep concept later on, okay, becomes like maybe like a sparking, source of the ResNet, okay, residual network, okay, which we will talk about, okay, in the next chapter. If you know ResNet, okay, you will know like how important that concept is. Okay, so basically, what is this wide and deep neural network is? Let me show you, the figure, which is much easier to understand for you. Okay, so you have this input, and this input, without looking this path, without looking this second path, okay, it looks just like a regular MLP. Okay, this input goes through the hidden layer 1, hidden layer 2, okay, and then go to the output layer, right? But, okay, here's the interesting part. Okay, this input actually has a second path. It goes, directly to here. So you can see that this data, this input data, actually has two paths. One goes through here, okay, one goes through here. We call this path deep. We call this path wide, okay? actually, okay, later on when you learn the residual network or ResNet, this path is sometimes also called skip connection because it skips several layers, right? It skips several layers. So what is the interesting part of this network? Okay, when Dr. Zheng proposed this idea, he said, okay, that okay, some features are better to be processed by multiple layers, multiple hidden layers. But some features, especially the simple ones, are better to be extracted directly from the input layer. Okay, so you can consider this path is good for the more hidden feature, the more complicated feature that need certain computation to extract it. And this path, this white path, is good for those features which are relatively easy, okay? And the most important thing is for those simple feature, okay, if you try to have those simple features to go through the hidden layers, sometimes you may break because of the extra additional computations introduced in the extra layers. I mean, it may break those simple feature. It may hurt basically like damage those simple features. So that's why the Dr. Zheng proposed this idea. But later on, as I said, okay, in a residual network, this idea, okay, is no longer considered that simple. Okay, we call that skip connection, and the whole idea becomes what we call residual learning. Okay, but so this is kind of like before ResNet was introduced. Okay, an interesting idea, a very interesting idea. Okay, so but obviously, okay, if you try to use a sequential API to create this model, you will encounter issues, right? Because sequential API doesn't do the model with multiple paths, right? It just doesn't work. Okay, so what do we do? Okay, so we can use what we call functional API. Okay, so let's assume this model is for the California housing problem, the same problem that we just mentioned. Okay, that is a regression model, right? So here, okay, you can see this is how the functional API work. Okay, so input equal to this one. Keras _layer _input shape. Okay, also we specify the shape of the input. Okay, and then the interesting part starts from the second line. Of course, I mean before that you can see that we didn't create a model object first, right? We didn't create a model object first, and we didn't wrap this thing into the model constructor either. Okay, so we first create this layer, and then the interesting part is the second line. Okay, you see hidden one equal to Keras _layers.dense 30. Okay, well, so it contains 30 neurons, and we use redo activation. So far so good, but the most important thing is here. Input. You can see that we sort of tell this hidden one, okay, is going to use the input, this input layer as its previous layer. And we actually pass this layer as argument, okay, at the end of this layer, so that we indicate that, okay, this input layer is the previous layer of the hidden one. Okay, and then, okay, for the hidden 2, okay, for the next hidden layer, similar things. Okay, we create a layer with 30 neuron activation, reroute, and then we know the previous layer of this hidden 2 is hidden 1, right? So we put hidden 1 as the argument here. So we sort of treat this whole, layer construction statement like a function. Because, well, we provide the argument, at the end, right? So this is exactly what I was mentioned. Like we treat, this is why like this approach is called like a functional API. Okay. And then, okay, the next layer is concatenation layer, right? Concat. So in the concat, this is where we need to, have these two paths joined together, right? So what do we do? Okay, concat equal to Keras.layers dot concatenate. Okay, so we have a specific, function that we allowed us to create a concatenation layer. Okay, what concatenation layer does is basically just put everything together, okay, into just one layer. Put them together. Okay, that's concatenation. So, but here you can see its previous layer contains hidden 2 and the input. Okay, so we can put like we can have like a multiple inputs, multiple layers to be the previous layer in the functional API. Okay, which was not possible in the sequential API. Okay, and the rest of the thing is pretty much straightforward, right? So we just like, the output is just Keras layer dense. Okay, we have one neuron because this is a regression task. And the previous layer is concatenation. Okay, and then, okay, now is a time to create a model. Okay, so, if you are using the functional API, after you, specify the relationship between each layers, okay, then here, okay, you create a model, okay, model equal to Keras.model, okay, but here, okay, you need to specify which is your input layer, which is your output layer, okay. If you don't have this line, you don't have a model in a functional API, even after you specify the relationship between different layers. Okay? So, I think I already explained like this stuff, so I will just go over them very quickly. Okay? And, okay, so you can see that, come back to here. Okay? So, when I say, okay, we need to specify the input and the output when we create a model, okay, it actually implies, okay, it allows us to have like more than one input or more than one output in our model. Okay, let me show you, okay. For example, okay, let me show you the figure. Okay, maybe in our features, after we've processed the features, okay, we know certain features are simple features. As I say, those should go through the wide path. And the other features are, hidden features, more complicated ones that need to go through like a deep path. So you can break the feature into two sets. One is input A, one is input B. Okay? These two different set of features do not necessarily need to be disjoint. Some features may appear in both input A and input B. That's fine. That's totally fine. Okay? the more important thing, this is just an example. I just want you to tell you, okay, the functional API is able to deal with like, multiple inputs. And, in sometimes, I mean, when you want to create like a model with like multiple inputs, I mean, this is like one of the reasons. And, here, okay, we do need to, make sure our data set, okay, to be processed so that, we have input A and input B in place, okay, and here, okay, so this is like the Keras API, functional API to create this model. We have the input A layer, okay, which is actually wide input. I mean, that does not go through like hidden layers. And we have input B, okay, we call it deep input, okay, and we have two hidden layers, and this first hidden layer use input B as like its previous layer. The second hidden layer use the hidden one, the previous hidden layer as its input, okay, and then, okay, again we concatenate, okay, the input A and the result hidden 2, okay, by using the concatenation layer, and then the other part are the same. Of course, like you also need to make sure that your data, okay, to be processed so that it has multiple inputs, okay. So you can see here, okay, we create like a training set for the input A and the input B, okay, not only for the training set but for the validation set, test set, okay, we need to create all this. And if you look at this code carefully, you will see the thing I just mentioned, okay. Actually, the features in the input A and the input B are not disjoint. Okay, there are some features that actually appear on both input A and the input B. And then, I mean, we can do the model fit, okay. We need to compile a model first here. We use MSE for training, for loss, and we use the SGD, and then we use the model.fit, okay. But here, okay, we need to make sure, okay, to provide the data set in the right format, okay. And the same thing, okay, the validation set also need to have input A, I mean both A and B, okay. But because we only have one output, so we only have one validation, okay. The output is, or put it in another way, the ground truth is the same, okay. We only have one ground truth, so the other part is pretty much similar to what we have seen previously. Okay, so this is for the multiple input example, okay, that obviously, I mean, if you don't use functional API, you cannot do it with the sequential API, okay. And we could possibly have like a multiple outputs as well. I mean, for one model to have multiple outputs. What scenario do we need to do that? Okay, there are two possible cases. The first case is that, okay, sometimes, okay, you want one model to do two jobs. I mean, normally you will create one model for one task, right? This is the simplest approach. One model for one specific task, okay? But if you want to complete two jobs, okay, together, okay, and you create two models, obviously, like, and it happened, if these two models happen to use the same input, okay, and then, running the two models obviously is going to take more time, right? It's going to, be slower than one model, right? Okay, so if you are able to use just one model to complete like a 2 tasks simultaneously, wouldn't that be nice? Because it will save you some time as well, right? So one example here, okay, is like, okay, for example, if you want to, you know, use like, you know, recognize the face. Okay, so for example, I mean, the input is a person's face, and you want to classify the person's facial expression. So this is a classification task. Okay, if this person is smiling, he's sad, or well, he's crying. You know, we want to, I mean, be able to classify, that face into several different classes. But at the same time, okay, we want to identify if this person is wearing glasses, okay, and which obviously is a binary classification task, right? And both tasks obviously, will use the same input, okay, the face, okay, as the input for the model, right? You could create, like as I said, you could create 2 models, one for each task, but running this is going to take a longer time. So as I said, you could use you could just create one model and have multiple outputs, okay? And so this is obviously one reason, okay, for a model to have multiple outputs. The other example is that, okay, sometimes, okay, we could use like the additional output as a regularization technique. Okay, remember regularization, what regularization, I mean, is? Okay, we talked about the like L1, L2, right? Previously, right? So basically, the regularization idea is to put certain constraint to the freedom of the model, right? Because sometimes the model is too, what should I say? It has too much freedom, so it overfits, right? The model overfits, and the regularization idea is just to constrain the model so that it is not as free as indicated by the number of parameters. So here, okay, if you have more than one output, okay, you can use one of the output, okay, as you can confine that output, okay, put certain constraint to that output, and then so that, I mean, it will put some constraint to the parameters in the model. So this is, a regularization technique. Okay, so in next chapter, when we talk about CNN, we will talk about Google Net, okay, which is the model Google created to classify, images, okay, in the ImageNet competition, and in that model, they use this idea. Okay, they have like they actually have more than one output. They have like several additional outputs, and they use those additional outputs as auxiliary output to regularize the network. Okay, so this is like another situation that you may want to consider, like more than one output. Okay, so here, okay, let me show you the figure first. Where is it? Here. Okay, I mean, here in this figure, okay, not only we have 2 inputs, okay, but we have 2 outputs, okay. The reason for 2 inputs I already mentioned, okay, previously. But for these 2 outputs, as I said, like this one is the auxiliary output, and which can be used for regularization purpose. Okay, so what do we do? Okay, that's for input. Okay, here is the code. Okay, the other part are identical to the multiple input one. Okay, so we only show the code that are different. Okay, so we have the output, which is the primary output. Okay, I mean, which is like pretty much the same. Okay, because it used the concatenation layer as the previous layer. Okay, but we have this one additional output. We call it aux output. Okay, and it has like 1 neuron. We call that aux output. Okay, which is like use the second hidden layer as the previous layer. And the most important thing is in the model, when you create a model, okay, you can see you need to specify not only 2 input, but also 2 outputs. Okay, and so because you will only have like you will have like loss function, right? You actually can have like a different loss function. When you compile the model, you need to provide the loss function for each output layer. Okay, so for the primary output layer, we use MSE. For the second auxiliary output, we use MSE2. And but we need to specify the loss weight. Okay, what is loss weight? Basically, loss weight, okay, is like a mechanism to put like a emphasis on different loss. Okay, so after all, the first output is the primary output, right? So this is the most important, important one, okay, for the model. So we want it to be as accurate as possible. So we put 0.9. We want to put more emphasis on the first loss, and we put like only like 0.1. A lighter emphasis on the auxiliary output. Okay. So of course, like you will also need to, prepare your data so that like you have like the ground truth. Now we have 2 how should I say, like 2 ground truths. But luckily, okay, because we are actually going to use the same value for the ground truth of these two outputs. So you can see that here. Okay, we don't need to do anything else. Okay, just in the model fit. Okay, we have 2, training set A, training set B. Okay, and we just repeat the Y train as our ground truth. Okay, this is the ground truth for the primary output. This is ground truth for the auxiliary output. And we train this model for 20 epoch. Okay, and for the validation data, same thing. Okay, we have the validation set A, validation set B, and we repeat this validation ground truth like here. So that's it. So the other part, pretty much the same. Okay. So just want to show you, okay, if you want to create a sequential model or like a feed-forward model, okay, or a simple one, okay, the simple models, okay, the sequential API is good enough. But if you want to create a complicated model, okay, then the functional API is a good one to use. Okay, it can accommodate like many complicated, cases. And no matter, if you can draw the model, pretty much, you can use functional API to create it. Okay, but we have we actually have third way called subclassing API. Okay, in Keras to build the model. So what, as I said, like I already told you, no matter how complicated the model is, we can use, as long as you can draw it, we can use a functional API to create it. Why do we need a third one? Okay, the third model, third type of model construction, okay, subclassing API, is used to build what we call dynamic models. Okay, what do we mean by dynamic model? Okay, it is the case like when you do the model training. Okay, during the model training, you are able to change the architecture, the structure of your model. Okay, so the model structure can be changed dynamically, okay, during training. So it is very powerful, okay, obviously. And but at the same time, okay, it is also, easier to make mistake, okay, and it's more complicated, okay, than the sequential API or functional API. Okay, so let me put it this way. Okay, if your model is a static model, if you are going to use the same model architecture, during training, during inference, pretty much like just stay with the same model architecture. Okay, so that's when I say model is static. Okay, in that case, use, depending on what the model architecture you have, like you can use sequential API or functional API. You don't use subclassing API. Okay, the only situation you need to use a subclassing API is when you want to create a dynamic model. Okay, which obviously is even for the state of the art deep learning paper that we have surveyed. Okay, there's almost no paper that is based on dynamic model. Okay, I'm not saying there's none, but the chance you need to use dynamic model is very rare. Let me put it this way. Okay, so let me give you an example. Okay, so you can create a class, okay, wide and deep model. So okay, so it's subclass the Keras star model, and here, okay, we need to define this. We have two primary blocks. The first one is like here. The second one is the core function. In a diff, pretty much you specify what layers you have in your model. Okay, so you can see that we have like 30 neurons, activation rerule. Okay, this KWARGS just means like that's like the input. Okay, the argument. Okay, and then we specify for example the first dense layer, second dense layer. Okay, and the main output, auxiliary output. Okay, so we specify all those here. But the relationship between these layers will not be specified until in the core function. So you see, so we have input A, input B as the inputs, and we have like this hidden one, which use input B This part is similar to functional API, yes. We use input B as like a previous layer of hidden one, okay, and so on. So, but the more important thing is we specify the relationship between between layers in the core function. Okay, of course, for this example. Okay. So, of course, when you create a model, okay, you want to train a model and evaluate the model, okay, and but this process sometimes can take a long time, okay, and so it is very important to know how to save or restore a model, okay. So this here, for example, when you create a model, okay, after you compile and feed the model, you can use model.save, okay, and specify the name of the file name, okay, to save the model into, okay, and the Keras will save the model using which is called like I think like you will use HDF5 format to save the model architecture and the value for all the model parameters. So obviously you can also use like Keras.models.load model, okay, to restore the model from the saved file back to your model object, okay. So but keep in mind, okay, these things work for the sequential, the model that is created by either sequential API or functional API. But for subclassing API, if you use subclassing API, unfortunately, it's more complicated, okay, because as I said, okay, the model architecture, okay, in the model that is created by the subclassing API is not, that easy to be obtained by Keras. So well, it is much more difficult to save and store a model that is created by subclassing API. This is also this is also another reason, okay. If you are not using a dynamic model, you should not use a subclassing API. Okay. And it is, when you create a model, it is very common that the model training takes hours. Okay. To be honest, like in my lab, like sometimes, I mean, when we work on a model, okay, the model, each training can last for like not necessarily, not only, but like a couple of hours, but like a couple of days. Okay, it could be that long. Okay, so yeah, this part, I mean, you can, if you use model subclassing, okay, you can use save weights and load weights, okay, to at least save and restore the model parameters. Okay, but you need to do all this by yourself. Okay, so this is not as convenient as like a model created by functional API or sequential API. Okay, so if your model training takes like several hours or even days, okay, so what do we do? Okay, sometimes we want, because I'm not sure. I mean, have you ever had the experience? But you guys are pretty young. I mean, so when I was in United States, okay, I mean, there's one occasion, okay, it took me like, almost a week to work on a project, okay. I still remember that that class is computer graphics. Okay, I'm not sure if you know about this, because does our department offer this class, computer graphics? Yes, but I'm not sure like the computer graphics you guys are learning today, okay, is the same as the one that I learned like back to, that was like 1994, 1993 or 1994. Okay, that was a long time ago. I think it was before you guys were born, right? Right. Yeah. So I'm too old. Yeah. You don't need to remind me. Yeah. So, yeah. So basically, like we need to
write, in computer graphics, I mean, that's the nature of the class. I mean, you just need to write a lot of code, okay, for almost a week. And just before the due day, okay, the computer crashed. Okay, computer crashed. So all my data files are gone. Okay, so what can I say? So yeah, of course I got a very poor grade. Okay, but the important thing to tell you is that, okay, when your model training takes hours or even days, okay, the most important thing is don't trust your computer. Okay, the computer can crash, very often, like, especially if you are running Windows, So, the important thing is that, okay, we have a way, okay, to keep the intermediate, result of the model training. It's called callbacks, okay, or checkpoints, okay. Checkpoint is like, when you are doing something, you save the intermediate, results. Okay, we call that checkpoint. So in the case, like, if something catastrophic happened, we call that rollback. You can restore the latest, results. So this in Keras, it is called callbacks. Okay, so this is okay. So you can use a validation set, okay, during training, right? We use that all the time. So you can set safe best only equal to true. If you set up the callback like correctly with this argument like that, then it only saves the model with the best validation result during training. So which is very nice, okay. So let me show you like the example. Okay, so first you create checkpoint. Okay, CB just abbreviation as for the callback. Okay, so this is actually an object. Okay, the model checkpoint object, which is a callback object. Okay, and you provide the name or the file that you want to save your the intermediate result to. Okay. And you specify save best only to be true, okay? So that it will save the best model that you have so far during the training. So here, okay, for example, you can start, using the model fit to train your model, okay? So here the epoch is only 10, okay? But if you set this thing, okay, like that, then you can. It's okay to have a much larger epochs, okay, because like eventually, okay, this place is going to keep like a much better, the best model that you can have anyway, okay. So after the training, okay, after you specify this, okay, of course you also provide the callbacks, okay, which is this checkpoint callback, and then okay, you just let the computer run and you go to bed. Okay, so next morning when you wake up, okay, the only line you need to run is this line. Okay, you just load the model from this place, okay, back to the model, and you are going to have like the model with the best performance. Okay, so which is nice, right? So. So remember the early stopping idea that I talked about like last chapter, right? So this is somewhat similar to that, right? But the only difference is that, okay, it doesn't stop, right? In the early stopping, like for example, like when the validation result getting worse and worse, you are going to stop the training, right? That is why we call it early stop, right? So yes, we can actually use the callback to implement the early stopping, and this is actually the more standard way in deep learning to implement the early stop. So it's like this, okay? So
we can have like a, early stopping callback object, okay? And here, okay, we set the patience to be 10. Restore best wait to be true. Okay, this is the same as like what we just mentioned earlier. So as for this patience, this patience just means like, okay, say we already hit this the lowest like validation loss. Okay, if it doesn't go any lower than this one, after the next 10 iterations, then the training will be killed. The training will stop. Okay, so this patience basically control like how many additional iteration you want to wait to see if because as I say, like the validation loss can fluctuate, right? So you want to wait for a few more iteration to see if it eventually go down, right? So this 10 just means you want to wait for the 10 more iterations to see if your validation will be will actually go lower than what it has been recorded, to be the lowest. Okay, so if that happens, okay, you are going to obviously, save the best model, replace the best model with the even better one, and then recount that 10 times patience. Okay, so with that, you can see we set epoch to be 100. You can set very very big epoch number anyway, because it doesn't matter. Most of the time, it's not going to run this long anyway. So because the training will stop. Okay, because of the early stopping anyway. Okay. So you specify the checkpoint callback and early stopping callback. Both of them. And once you are done, okay, because you set up this early stopping callback, so the model will automatically be restored to the best one. So this is like how the early stopping is implemented in deep learning. Okay. So I think I already, mentioned about the idea here. But there are many other callbacks available, okay, in Keras.callbacks package. So this is like, if you want some the Keras to do some side works for you, okay, at a specific moment, you can check out like some callbacks that that sometimes they can help you a lot. So, for example, if you need extra control, okay, you can even create your own custom callbacks. This is an example, okay. How we can do a custom callback. This custom callback, okay, is just going to the print the value for the training ratio, okay, for you, okay, at end of each epoch. Okay, so what you can do is you subclass the callback. Okay, you call this a print val train ratio callback. Okay, and here you define, okay, on epoch end. So this is at the end of the epoch. Okay, so you want to print this value. Okay, this value, sometimes can help you to observe like the training progress. Okay, because it print out the validation loss for you. Okay, pretty much. But so you can see that this statement will be executed. Okay, if you include this callback, this statement will be executed at the end of the epoch, right? Obviously. So you may ask, so what occasion, other than end of the epoch, in what other occasion can I have my statements executed? Actually, there are so many, different places you can run your code. Okay, for example, on train begin,
on train end, that's at the beginning of training or at the end of training, on epoch begin, on epoch end, on batch begin, on batch end, you know. So there are so many places you can do these things. Okay, so this allows you to have the control of many things to do at a specific time. Okay, when you are training the model. Okay. So next, probably 20 slides. Okay, is about TensorBoard. Okay, what is TensorBoard? The TensorBoard is a tool. Okay, this is a visualization tool that help you to visualize your model. In addition to that, you can check like a model architecture, model like a weight. For different layers. You can even check like the learning curve. Okay, when you train the model. Okay, it actually draw all those visual results dynamically. Okay, when you're doing the training, it will generate those visualization results. So it's very nice tool to have. It's a very nice tool to have. But on the other hand, okay, I kind of feel like this is kind of like some extra tool, okay, for you. Which you don't necessarily need to use it. Okay, if you know it, great. If you don't know about it, you can still, write your program very well. Okay, but obviously this is a good tool to know. So if you want. If you want to have your model to be visualized, okay, then you import this and provide this use this code, okay, because you need to specify, okay, the place where you store those intermediate results so that the TensorBoard can draw the visual result based on this text results. Okay, so for example, okay, after you specify, the directory. Okay, so if you get wrong log directory, it will give you like this. Now this is basically specify like this is a run, okay, of the model, at a certain time, okay, So with that, okay, first you have this function defined, and then, okay, you create a TensorBoard callback, and you provide that function as an argument of this object, so that you will save the intermediate result, okay, into the appropriate place, okay, and then when you do the model fitting, okay, you provide this callback, okay, so after that you can use the TensorBoard to visualize the result, okay, and so here, okay, it shows you like the architecture, the structure, okay, of like the location that the intermediate result is saved. You can see like at a different run, at a different training instance. Okay, all these things will be saved. Okay, including the training as well as the validation results. Okay, and here it shows another training. Okay, and you have additional results here. So it's going to save a lot of like this intermediate stuff. Okay, and once you have those intermediate results, okay, even during training, okay, you can file the TensorBoard. TensorBoard is actually a program, okay, that use like a web service to provide the visual result. Okay, so it's kind of like Jupyter. Yeah, Jupyter is also like that, right? Jupyter is actually like it provides the service through the web, like interface. Same thing for the TensorBoard. So you run the TensorBoard, it will tell you, okay, TensorBoard, okay, it is at this, basically this is localhost, okay, and the 606 port, okay, and then you can have your browser pointing to this website and to observe like the visual result. And sorry, here, okay. So and also if you are in Jupyter, okay, you can also use where is it? Yeah, in the Jupyter you can also initiate the TensorBoard by typing these statements. Okay, so this is like how you start the TensorBoard, and the most important thing I want to show you is, so this is like what the TensorBoard looks like. So it's a very fancy tool, and you can see you can even like have some control over like the visual result you wanted to demonstrate, and yeah, and this one obviously shows like the learning curve, okay, and I just want to tell you, okay, this thing is so cool that it actually while you are training, okay, this thing can collect the result from the training and draw it dynamically. You don't need to wait for the end of the training to draw this. No, you can just start this TensorBoard and observe this learning curve, like to create like on the fly. Okay, so it's very nice. Obviously, you can also, if you already have some model that was trained previously already, you can also like select a certain log to show like the learning curve. So it's an interactive visualization tool. Okay, so so you can also visualize the whole graph. Okay, the learning weights, okay, everything, okay, from the TensorBoard, okay, and TensorFlow also offer a low-level API, okay, in tf.summary package. So this one, okay, creates a summary writer, okay, which will write a, use the create file writer function, use it to write a context to log scatter, okay, histogram, image, audio, text, okay. So you can, all this you can, basically visualize using TensorBoard. So here I just provide a code for you, but to be honest with you, like I'm not that much of a big fan for visualization tool, even though I know it's a convenient tool to have, okay. But you guys can try, okay. But I kind of feel like as long as I get like those like training accuracy, training loss, and validation accuracy, validation loss in text, I'll be satisfied, okay, most of the time, okay. But obviously the visual tool is a good one to have, okay. So in summary, okay, so this TensorBoard is a nice stuff to know about, but so you can invest some time to get to understand it better. And also, we have learned, where a neural network come from, and what is a multi-layer perceptron, and how you can use it for, okay, such as classification, regression, and how to use sequential API, functional API, subclassing API, all this. And we also talk about how to use, for example, like how to save the model, how to use checkpoint, how to do the early stopping, and in addition to those things, I mean, the tensor board, okay? And, you know, but we obviously have many hyperparameters we can tune, okay, when you train a model, okay? So this actually has something to do with, you know, the performance of the model. I mean, because I just got a student asking me like, you know, oh, my performance, my MLP performance is not as good, okay? So the first suggestion I will tell you is basically like there are many hyperparameters that you can tune, okay, to get a better performance. You know, there are other things, but you know, we can start from the hyperparameter tuning. Okay, so what are hyperparameters? Okay, for example, okay, the hyperparameters, I mean, include, okay, for example, the number of layers, number of neurons, I mean, in each layer, and the type of activation function, and the weight initialization. They are. I mean, right now, I mean, a lot of this we really haven't talked about that in depth, no, and other than those, for example, like learning rate, okay, or like optimizer. So far, the only optimizer you are familiar with perhaps is like SGD, right? So there are other optimizers out there that can help you to get a much better performance. So you know, what hyperparameter value should you use? Okay, I mean, so this is, I mean, you know, we want to talk a little bit about this, but we will go into much deeper on this topic in next chapter. Okay, but now we just, you know, a quick, like try to give you a quick overview of this hyperparameter selection. Okay. Of course, if you are trying to just like okay, just want to find like a good combination of those hyperparameters, one way to do it is to use grid search. Okay, grid search basically just, you know, grid search, right? Basically like just, for example, like okay, you want like to see how many layers is good. Just 1, 2, 3, 4. Okay, try all the 4 combination, four types. And if each layer you don't know how many neurons, okay, you can try 100, 200, 300. Okay, so you have 3 options for number of neurons for each layer, and you have 4 options for the number of layers, right? So 3 times 4, 12. Okay, so this is grid, you know, grid search. Pretty much grid search is like that. Okay, and but the grid search, obviously, when the number of parameters increases, okay, obviously, because you are going to have many options to try, many combinations to try, right? So maybe, because for each combination, it takes time to train the model. So maybe it's not an ideal approach. So another approach is to use a randomized search. Randomized search is something like, okay, you just randomly determine a combination. And if that combination gives you a good result, try to find like a combination near that, the other combination near that combination. Okay, so that's the basic idea of randomized search. Okay, so here, I mean, we use like, you know, give you like, this is like, you know, we can, you know, build, what is that? I mean, we call it like a grid search CV or randomized search CV, okay, to explore hyperparameter space. So randomized search normally will give you a better result in a shorter period of time, but you don't have, you cannot guarantee that that is the best value. Grid search, because it pretty much goes through all the combinations. I shouldn't say all the combinations, because maybe you just try like a 100 neuron, 200 neuron, 300 neuron. So it doesn't, it's not like a 100, 101, 102, right? So it doesn't give you like a all combination, but it gives you like a most of the combination. So you can you are more confident that the grid search result, the best one, is pretty good. But for the randomized search, it doesn't try all the combinations. So you spend shorter period of time to explore the search space, but it normally give you a better, a very decent result already. So this one just you can follow this example to try to use because you define a model, define a build model function like this, and then you can wrap it, okay, with Keras regressor, and then use it to try different combinations, basically, okay. So you can train the Keras regressor using different, values. So the previous one is for the grid search. This one is for the randomized search, and so you can see that you need to provide the parameter distributions. For example, number of hidden layer that you would like to try includes 0 hidden layer, 1 hidden layer, 2 hidden layers, 3 hidden layer. For number of neurons, it could be range from 1 to 100, and for the learning rate, okay, it could be from here to here. Okay, so basically you get an idea that this provide the range of the parameter space that we would like to explore. Okay, and you can use a randomized search CV over the Keras regressor that we just created. Okay, using this model function. Okay, to try all the possible parameter distribution. Okay, so this obviously take a lot of time. Okay, and so this is a randomized search. So it will give you like the best parameter, the combination of parameter. Okay, so by using the best combination of the parameter, you will get a better performance. Okay, from your model. Okay, so this is like something you can you can follow to if you want to try like if you want to find like a good combination of the hyperparameters for your model. Okay, so I think like I will go into much deeper about this hyperparameter tuning next chapter. Okay, so because these are kind of superficial. There are other techniques that you can explore search space. There are tools out there. For example, this HyperUp, HyperUs, KUps, Telos. They are all like either libraries or basically to help you to find like a good hyperparameter combination. Okay, so but those are, what should I say, not provided native by Keras. Okay, there are other, even like what's the name of that? I think that name is called Asker. Okay, there's like even like a web service. Okay, out there. In which you provide your model to that web page, and the web page will tell you the best combination of the hyperparameters. Okay, if I remember, it's called Asker, OSCAR. Okay, so there are many such tools, either, it's tool or like an API or web service that basically like try to tell you like, which hyperparameter, is better to use, okay? So, there are other Keras tuner, scikit optimize. So this one is, is built under the scikit-learn, okay? Hyperband, sklearn, deep, okay? All these things, they are basically tools that help you to explore search space, okay? So, or there are service, okay? For example, I think like Asker, yeah. The call desk Asker, remember I just told you, okay? So Arimo, SigUp, those are like, web page service that, provide like, provide you the service like to find like the good combination of hyperparameter, okay? So hyperparameter tuning is still active area of research, okay? So I think like I will talk about more about this in the next chapter, okay? So in the future, okay, the building neural network, okay, will soon be over, okay, because they are Google's post, okay? You can check out this post, okay? Evolutionary algorithms, I don't know if you are familiar with that. A genetic algorithm, in short, okay? They use genetic algorithm to intelligently pick up like the best hyperparameter combinations for you, okay? So you can check out like this Google post by yourself, okay? So there are guidelines. Okay, let's take 10 minutes break. When we come back, we quickly go through a guideline, and I really hope to go to the next chapter that we can talk about this in much more detail, okay? Okay. Okay, let's quickly go over these guidelines, okay, so that we can move on to the next chapter, okay? Okay, the first one is number of hidden layers, okay? So, basically you should start with like a small number of hidden layers. But in terms of parameter efficiency, okay, sometimes if you feel like, okay, the model is not complicated enough, I want to either add more number of neurons or add more layers, okay? If you have these two options, okay, then, okay, adding more number of layers normally will give you better parameter efficiency, okay? So, so shallow model normally has a much worse performance than the deeper one, especially, it doesn't matter like how many neurons you have at each layer, okay? And later on, when we talk about CNN, you will see like we actually, especially like at the, first like stage of the CNN development, you can see the model become deeper and deeper. Okay, this actually echoes this parameter efficiency argument. Okay, the
the deeper model has a better parameter efficiency than the shallow model. Okay, just want you to understand this. Okay, so one way to explain why this is the case is that, okay, for example, say if you want to draw a forest, okay, using some drawing software, okay, but you are forbidden to copy and paste anything. Okay, it will take an enormous amount of time, right? So basically, you just like have to draw everything like one stroke at a time. Okay, but if you are allowed to do copy and paste, for example, then you can draw one leaf, and then you can copy many leaves to become a tree, right? And you can copy many trees to form a forest, right? So by doing this simple copy and paste, it allows you to finish the drawing of a forest in a much more efficient manner, right? So having like more layers is something like that, because the lower layer take care what should I say, like the more simple features, and the higher layer can focus on more complicated, more advanced features. For example, the lower layers normally can detect maybe like the orientation of a line, something like that. And the higher layer can detect maybe the shape, maybe like it's a rectangle, it's a circle, it's an oval, in the higher layer. So it actually, having multiple layers allow the model to divide the task into like a simple ones and a complicated one. I mean, by doing that, I mean, it will actually give you a much, more efficient model. Okay, something similar to like using copy and paste to draw a forest. Okay, so this is like just want to give you an idea. Okay, and once you understand this thing, okay, so the model, as I said, like the lower layer deal with like a more simple feature, the higher layer deal with more complicated feature. Then you can, immediately understand the concept of transfer learning. What the transfer learning is, okay, is you try to use a model that is doing a similar job for another task. Okay, for example, okay, say like if you have a model that can classify like different objects, okay, then you can transfer learning that model, because that model, okay, if I draw it, so this is the model. This is a model that classify, okay, different object. For example, okay, like a person from, I mean, you can classify. It's a person. It's a car. It's a cat. Many different type of objects. Okay, then obviously the lower features, the lower layers will deal with features that are more, more simple, right? Maybe like a line orientation, as I said, this is maybe the shape and so on. And eventually it is able to detect like, okay, this is like maybe like a human or like a car at a higher layer, right? So transfer learning, what transfer learning is, the basic idea is you just copy this model and you keep the lower part of the model intact. So you copy the lower part of the model. So this part is almost identical to the previous one. Why? Because
this say like now you want to this one is to classify different objects. This one maybe you just want to identify, maybe just identify like a different type of car. Different type of cars. Okay, so you know the lower layers is already able to distinguish, okay, it is car or something else, right? From this model, right? So you can copy the lower layers to here. But obviously, we are not able to identify, oh, this is SUV, or it's a sedan, okay, or like a sports car, So we need, you may need to add a few more layers. So these are the new layers. These are the new layers. New layers. Okay, so you do need to train these few new layers. Okay, but because you only need to train, for the whole model, okay, because you copy the lower part from this model. So all these layers, in addition, I mean, their weights remains. You can consider they are already trained. Okay, you only need to train these few layers, these few new layers. I mean, to be able to classify like a different type of cars. So what should I say? Like, you don't need so many training instances. The training set can be much smaller. Okay, and the training process can be much shorter. Okay, in fact, okay, nowadays, okay, when you want to train a CNN model to recognize to do something for you, okay, nobody train a model from scratch nowadays. Everybody do transfer learning. Okay, everybody's do transfer learning. You seldom see, I mean, that you need to train the whole CNN model from scratch, because, as I said, if you want to do that, then you need a big training set. And it takes long time to train a deep neural network, okay, from scratch. But now, I mean, since transfer learning, you only need to train maybe 2-3 layers at most. Then the training process is much shorter. Okay? So that's the idea of transfer learning, which has been used widely nowadays. Okay? We are going to talk about transfer learning, use an example to talk about transfer learning. Not right now, but in the next chapter when we talk about CNN. Okay? As for summary, of number of layers, okay, so for many problems you can start with just 1 or 2 hidden layers. So for example, like you can reach 97% accuracy on MNST data set. Okay, use just 1 hidden layer. Okay, and 98% accuracy using 2 hidden layers with the same total number of neurons. So with about the same amount of training time. So you can see, the deeper network give you a little bit higher accuracy. I mean, not by a lot, okay? I mean, the improvement is 1%, but of course this 1% is very nice. But, that's probably because like the problem itself is simple. But the idea is that you don't want to start from a lot of layers. Okay, for more complicated problem, you can ramp up the number of hidden layers until start overfitting the training set. So you can try to increase the layer, okay, until you get you have an overfitting problem. So very complicated task, okay, such as image classification, speech recognition, typically require network with dozens of layers or even hundreds of layers, okay, as we will talk about like in the CNN chapter, okay. So, but normally we don't, it's not fully connected. It's not real
MLP, because MLP use the dense layer that we have like a fully connection between the consecutive layers. But in CNN, it is not like that. Okay, so you really have to train such network from scratch, as I said. Okay, we normally use transfer learning. Okay. As for number of neurons, okay, you can, for example, for the input layer, it normally depends on your input set. Okay, if you have, how many features you have. Okay, pretty much determine a number of neurons in the input layer. Okay, for example, for the MNIST, okay, it's the input layer is 28 by 28, 784, because that's the number of pixels, right? Okay, for the hidden layers, the number of neurons, okay, basically it doesn't tell you exactly what number of neurons to use, but it tells you, okay, normally you are going to form a pyramid with fewer and fewer neurons at each layer. So it's actually going to be something like where is it? So it's something like this. So the higher layer has fewer neurons. The lower layer has more neurons. Okay, this is consistent with the concept I just mentioned, because the lower layer, remember, lower layer deal with a more fundamental features, right? More simple features, and you could have many simple features, but for complicated, for more abstract features, for example, the top ones, maybe it's already very close to or maybe it's a human or dog or something, So the top ones, okay, for the abstract features, you don't have that many abstract features. But for the lower layer, even the orientation, different orientation of the lines could be different features. Okay, so we have more new. It's suggested that we have more neuron at the bottom of the model. However, okay, so this example is we use first layer we use 300 neurons, second layer 200, third layer 100. So this is consistent with the pyramid idea that we just talked about. But the newer idea is that, okay, it doesn't matter. We can use the same number of neurons for all the layers. Okay, so which one is better? It's really hard to say. Okay, it's really hard to say. Because this one, okay, if you use a different number of neurons per layer, that means for, you need to have, you need to consider, okay, how many neurons we want to use here? How many neurons you want to use here? So you have a more number of hyperparameters to decide, right? Because each layer you have a different number of neurons. So you have more, each layer you have one additional hyperparameter, which is number of neurons in that layer. Okay. So too many hyperparameters may also be difficult, especially when you consider you want to do a hyperparameter, combination search, right? So some people nowadays they suggest, we just use the same number of neurons for every layer. Okay, the reason, the benefit of doing that is that, okay, now if you do that, then we only have one hyperparameter to decide, which is the number of neurons for all layers, right? So which one is better? As I say, it's hard to say. So, okay, recently there's one
another idea, okay, called stretch pants approach. I mean, what is this? Okay, it's like when you are little, okay, your parent buy clothes for you. They will buy a bigger clothes for you, right? And tell you, oh, you mean when you grow up, you mean the pants just fit just right. Maybe it doesn't fit right now, okay, but after like a couple months, okay, it fits perfectly, right? So your parents, or a lot of parents do that. I mean, take me as an example. I mean, because I have an elder brother, so I always get clothes from my elder brother. So it's a little bit too big for me, but you know, I get used to that all the time. But okay. So what is exact stretch pants approach here? Okay, basically it's like okay, it is okay to create a large model, okay, larger model for your task. Okay, you may create like a deeper network than necessary, or more number of neurons per layer than necessary. Okay, then you may wonder, well, then isn't that we are going to have like too much freedom to the model, and which will cause like overfitting easily? Yes, that's true. But remember, we have technique to fight with overfitting. We can use regularization technique, right? We have L1, we have L2, we have like auxiliary output. We have early stop, right? We have all sorts of like a technique to fight with overfitting. So you can use a larger model and then use regularization technique to confine its flexibility, it's a freedom, so that it fits right in. Okay, so this idea is called stretch pants approach. Okay, so I think in the next chapter we are going to talk about more techniques that fight with overfitting. Right now you don't. We only talk just a few of them. You don't have a full set of like techniques available for you for overfitting issue. But I will tell you. In the next chapter. Okay, and for the learning rate is also a very obviously a very important hyperparameter. Okay, so the optimal learning rate is about half of the maximal learning rate. But you may ask, what is the maximal learning rate, right? It seems like it doesn't say anything, right? So the maximal learning rate is the learning rate above. If you have a learning rate higher than that maximal learning rate, the training algorithm will diverge. So that's like the largest one that the model training will not diverge. So the optimal one is normally half of that. Okay, but it still takes time to search, right? It still takes time to search. So finding a good learning rate is, it's going to take time. Okay, but there are other techniques out there. Actually, you can adjust the learning rate like during training. Okay, so you can use a larger learning rate at the beginning of the training and gradually shrink learning rate when the training converge to the optimal place. So this type of concept is called learning scheduling. Okay, learning rate scheduling. We are going to talk about learning rate scheduling. There are actually many learning rate scheduling out there. We are going to talk about them in the next chapter. Okay. And there are also a lot of different optimizers out there. As I said, you guys only know the gradient descent, but there are many optimizers out there. Okay, that which actually has a big influence on the model performance. Okay, so we are going to talk about that next chapter. Okay, and also the batch size. Because as I said, we normally use a mini batch, right? So how big is a batch size? Okay, so well, the batch size. Okay, normally like it depends on the GPU. I mean as well, but normally we set the batch size to be 32. Okay, and there's an interesting comment from Yang Lechong. Okay, you guys know Yang Lechong, right? We talked about Yang Lechong. This guy, I mean, at the beginning of the class, I mean, this guy is now like the Facebook AI lab director. Okay, and he's a professor at NYU. Okay, New York University, and this guy is really good. Okay, as we will talk about in next chapter, you know, he is really a pioneer. Okay, of this deep learning. So in early 2018, okay, Yang Lechong comment that friends don't let friends use mini batch larger than 32. So he back up the idea, okay, that mini batch, you know, should be smaller or equal to 32. Okay, so I mean, there's a because he cited a paper, okay, 2018 paper from this bunch of people, and you know, this is also there are also some debates for this. Okay, some people prefer to use like you know, it was possible to use a very large batch size up to like you know, 8K using various techniques, and such as warm up at the learning rate and so on, and you know, etc. But in general, okay, let me put it this way, okay, Yang Lechong's suggestion, okay, work most of the time, okay, at least in a simple setting, Yang Lechong's suggestion is true, okay. So, and also I want to emphasize that if you change any setting, such as batch size, such as like you know, the network architecture, for example, like adding more neuron or change like number of layers, remember you need to, you know, tune your learning rate again. Okay, this is like something you need to remember. And activation function, number of iterations. For activation function, okay, right now you guys have only seen like a rerule, right? And sigmoid maybe, okay. But later on, we are going to talk about more different activation functions out there, okay, in the next chapter, okay. And for the number of iterations, if you use early stoppings, then the number of iterations is not an issue, okay. You don't need to worry about that. You can set it to be a very large number, and set an early stopping to let it like a training stop, like when the model, you know, is already converged. Okay, so so this is not the issue. Okay, so this is like the conclusion. So there are, you know, for more best training practice regarding tuning neural network hyperparameters. So there are like a paper from Leslie Smith that you can check out. Okay. So I think like there are also like you know, we can customize models using TensorFlow low-level API and how to, you know, load and pre-process data efficiently using the data API. Unfortunately, we are going to skip that chapter. Okay, we don't have time to go over every chapter in the textbook. We just simply don't have that much time. But that chapter, I think like the low-level API and like the API for like data preprocessing, I think I mean it's I think it's a chapter 10 or 12, I forgot. But I think you guys can check it out yourself. Okay, let me put it this way: take
take the other chapters, I mean, that we cover like without any problem, okay? So that's about it for this chapter. So that's, how much do we, time do we, okay, we still have like 15 minutes. What happens? How come it's 丘皮啊，你可以帮忙调一下吗？怎么又变这样子？因为我没有遥控器。遥控器。你这个可以帮忙？这样。很奇怪，就怎么变得这么？是变太大吗？还是？This is much better. OK， 这样可以，谢谢。OK。So, OK, in the previous chapter, OK, chapter 10, OK. By the way, I mean we just finished chapter 10, OK, and now we are on chapter 11. In chapter 11, OK. So chapter 11 talk about like how to train the techniques on how to train the neural networks. Okay, so so we although we try to train our neural network in the previous chapter, okay, but it's a very shallow DNN with only 2 hidden layers. So when you have a complex problem and if you want to create like a more complex model, and you may have like 10 layers, each containing hundreds of neurons, and you will find that, okay, simply using simply using the fit to train the model a lot of time doesn't work. Okay, it doesn't converge. Okay, it will not be a walk in the park. It's not that easy. Okay, so what are the problems? What caused the training to be difficult? Okay, the first one, okay, you would face the tricky vanishing gradient problem, or on the opposite, exploding gradient problem, okay, which will affect the deep neural network and make the low layers very hard to train. Okay, so this is like the first issue. The second issue is you may not have enough training data. Okay, you may only have like a limited amount of training data, but for a very complicated task. So what do?